All right, well, thanks very much for listening, folks. And as always, thanks, Ron, for putting together this great meeting. So that's the title. Here are my disclosures. Nothing particularly stupendous. Okay, so how do I get rid of that?
Just move it.
Drag and drop it. Drag it up out of the way.
Okay.
And then make sure you park your mouse somewhere that we don't see. You have the corner, yeah.
Yeah.
Keep sliding it over.
And you can
Take it over more.
Okay, you can see the mouse, which is good.
There you
go. Yeah, all right. Okay, so let's talk about the shortest trip to clinical usefulness, oscillometry. And we've heard plenty about that today. It is, you start by making a measurement of resistance and elastance using oscillometry, and then you go straight to these empirical parameters. Oh, you hear me okay? Yeah. You heard about them, R5, R20, the difference, X5 and AX. These are the typical ones that people talk about. And you use those to diagnose and prognosticate. Now, when we do this, it's a purely empirical exercise. We're not saying anything about what does it mean. We're no interpretation physically, physiologically, or medically. But it still can be very useful because you can say, well, R5 is higher than it should be. There's something wrong with this patient. But as I said, so far, we've imposed essentially no physiological interpretation on the measurements that we're making. And this is like a lot of evidence-based medicine. You know, you have treatment A versus treatment B. You do it in 100 patients in each, or 1,000 patients. You say, which group does better? You answer a binary question, A or B. And there's very little beyond that in terms of mechanism. Even though the question might be motivated by mechanistic knowledge, the actual question that's being addressed is not mechanistic. Now, if we want to be a little more enlightened, if we're sort of the mindset of this august group here, who is inclined to say, yes, but what does it mean? Then you have to take a little side trip from your measurements of reactance and resistance and explain them in physiological terms, but this requires some kind of model. There is no escaping this. And if you think for a moment that, oh, I'm not using a model to interpret it, well, yes, you are. Even if you think about airway resistance is assuming all this massive piping here is one long tube. So there's some kind of model involved. And then you go from there, hopefully in a more enlightened way, a more insightful way to do your medical assessment. So let's think about some of these models. The simplest reasonable model of the respiratory system is a balloon on a pipe. The balloon has an elastance E related to the measure of its stiffness. The pipe has a resistance R, which is reflected by its caliber. And it also has an inertance I, which is due to the mass of the gas in that pipe, which has to be accelerated backwards and forwards. This model has a precise mathematical equation. It looks like that. Some of you may have seen it. Still staying in the realm of mathematics, you can calculate the impedance of that model. It's this here. There's a real part R, and this thing in the square brackets is the imaginary part. And what that looks like, if you were to draw it, is this. You have the real part, the resistance on the top, the reactance on the bottom. And now if we impose those parameters that I was just talking about on this model, on this impedance, R5, the resistance at 5 hertz, is simply equal to R. And so is the resistance at 20 hertz. So there's no difference between them. The reactance at X5 comes from evaluating this term in the square brackets at a frequency of 5, and that's what it is. It's 31.4 I minus E divided by 31.4. The resonant frequency you get by solving for F within the square bracket. That's the formula for resonant frequency. It's proportional to the square root of elastance divided by inertance. Now you're saying, but can you tell me what AX is? Yes, I can. The good news is I can. The bad news is that's what it is. And that comes purely from solving that equation, just using a little bit of calculus. And you see that AX involves E and it involves I. Now, it turns out if you do a sort of sensitivity analysis on that, for a given fractional change in E, you'll get a bigger change in AX than for the same fractional change in I, the typical values of E and I. Which means, in a hand-waving kind of way, that if you say that AX is a reflection of elastance, stiffness, you're basically in the right ballpark. But it's not purely elastance. Okay, now, this model cannot account for the well-known observation of the negative frequency dependence of resistance. It's not possible to do that. So how do we do that? We have to use an extended model. The one that's usually invoked consists of two compartments like that, connected in series. What are the anatomical identities of these? Well, that's a key question. This E2 here is the tissues of the lung and the chest wall for sure. This E1 is the equivocal bone. It could be the stiffness of the central airways, or it could be the stiffness of the cheeks here. My suspicion is, if you're dealing with a model like this, it's mostly the upper airway stiffness, but more investigation has to be done before about it. And this model, this series 2 compartment model, is why we tend to think that R20 reflects distal airways and R5 reflects the sum of the two. But I want to caution you, that's not necessarily the case. It may actually be quite wrong. It could be that when you get frequency dependence here, it's because the overall airway resistance R2 is increasing, which is causing shunting into the central airways. So this central versus peripheral airway resistance is equivocal, to say the least. But things are more complicated than that because you can also have heterogeneities in a parallel sense, like we were talking about before. So two balloons on two pipes going off to different parts of the lung. Now, I did a little simulation here. We have a common airway R1. Let's assume this is a homogeneous model. R2 is the same in both cases. E is the same in both cases. So that looks like a single compartment model. I then calculated what happens if I take one of these R2s and I increase it by a factor from 1 up to 10,000. By 10,000 increase in resistance, basically it's complete closed. What you find is that the overall airway resistance at the three different frequencies, 0.1, 1, and 10 hertz, shown by the color codes, do this. They all go up to a peak and come down. The peak is at different points. And they come down. By the time you got to 10,000 increase in resistance, you're back to a smaller homogeneous line. Elastance does this. And the ratio of airway resistance to elastance in all cases starts by increasing. And this is quite well-known idea that resistance increases proportionally more than elastance in the face of heterogeneity. But that's only up to a point. Eventually, when the heterogeneity becomes severe enough, it decreases again. So these are the sort of behaviors that you can get with a simple model like that. Now, another thing that can happen, which is a sort of phenotypically distinct from airway narrowing, heterogeneous or uniform, is alveolar closure. I'm going to call it diffuse alveolar closure or collapse, maybe caused by actual closure of small peripheral airways. Here it gets kind of interesting. Let's say we have a two-generation airway like that with 4 alveolar compartments. And to begin with, it's perfectly uniform. We have R1 and then 2 R2s and 4 R3s. Now imagine we close half of those alveoli. Oh, by the way, if each of the elastance of each of those alveoli is E, then the total elastance is E divided by 4, which you're dividing the volume going in amongst 4 compartments. And this is what the airway resistance is. It's the series sum of R1 plus the 2 R2s plus the 4 R3s. You get this. Now, let's suppose that we block off C and D so that only the red pathways are open. The elastance is now EL over 2 because we only have 2 alveolar compartments, and you can add up those 2 pathways. It's R1 plus R. It's R1 plus R2 plus R3 over 2. But we can have 50% closure by closing closing A and D and allowing B and C to be open. And now the airway resistance is R1 plus R2 over 2 plus R3 over 2. So in fact, the resistances are different, but different patterns of the same degree of elastance increase, which just shows you that the whole interpretation gets a little bit complicated. Now I'm going to jump straight to a simulation of a more anatomically reasonable lung. And here I have a model of a lung that ostensibly includes every single airway in the airway tree. It's specified according to the Horsfield asymmetrical branching pattern, where airways are designated according to their order. So terminal bronchioles are order 1, then order 2, order 3, all the way up to order N of the trachea. In this case, N is 25. At every branch point in this airway, the difference in order between the two daughters is a fixed number, which is called delta. And for a human airway tree, delta is about 3. For a mouse, it's about 6. Mice are more heterogeneous than humans. So the parameters of this model are the total number of airway orders, the delta that I just described, I have a fixed ratio of airway length to radius, which is 6, which is about right with the literature. An airway radius of order K is smaller than, is bigger. No, let me put it. An airway order of K minus 1 is smaller than an airway order of K, so going up in order, by a fixed fraction of gamma, which is about 0.85. So it's a geometric scaling of the airways. They're getting smaller by the same fraction as you go down. The tracheal radius is a parameter of the model. And also I make the tracheal length longer by a factor of 4 than it would be if it followed that scaling scheme that I was talking about before. So, and we have, so the first 1, 2, 3, 4, 5, 6 parameters completely specify the airway tree. And then on the end of every terminal bronchiole, I have a respiratory system elastance, actually a constant phase unit, with an elastance H. So that specifies, with a relatively small number of parameters, the complete mechanical properties of an entire airway tree with its parenchyma. I assume I can get a tissue resistance out of it as well, and then I have to use the viscosity of the air and the density of the air in order to calculate resistance and inertance. So what I did with this model, I did a Monte Carlo simulation where I would randomly start out with a baseline configuration that I just described, and then I would randomly narrow every single airway by a factor that in the green curves there was up to 20% of its nominal relaxed volume. So in other words, you have a uniform, symmetric and non-heterogeneous airway tree, which is the control situation. And then you go through in every single airway, you pick a random number and narrow it anywhere from no narrowing to 20% narrowing spread across the whole airway tree. That's the green. Or anywhere from nothing to 40% narrowing, that's the blue, or anywhere from nothing to 80% narrowing, which is the red. So in other words, as we're going green, blue, red, we're getting increased heterogeneity of narrowing throughout the airway tree. And what you can see here is that for the control 20% and 40%, there's basically no difference in reactance. There's a little bit of a difference in resistance. When we get to 80% random narrowing, we get a big jump up in resistance, a big jump down in elastance or reactance, but it's not as big proportionately as the increase in resistance. And also notice you're getting this negative frequency dependence here due to the heterogeneity. And what I'm showing by the solid lines is the best fit of the single compartment model, which of course assumes that resistance is constant. Now, the interesting thing is if I do the sort of phenotypic converse of this, which instead of narrowing the airways, I randomly close alveoli. So I go from a random narrowing to a pure de-recruitment model. Now using from 20% control, 20% closure to 40% closure to 80% of the alveoli are closed, we get these progressive changes in resistance and reactance. But you notice the pattern's kind of reversed. The big effect is now in reactance. And even though you get an effect in resistance, it's proportionately not as great. So if you think of airway narrowing versus alveolar closure as two phenotypic extremes of the physiological spectrum, they show up with a different kind of signature in a model like this. So you can't say for sure whether you've got one or the other or what the proportion is. But if you do an intervention and your big effect is in elastance, that's more compatible with the idea that you're looking at a diffuse de-recruitment phenomenon than narrowing and the converse. If I do this a little bit more extreme, and oh, by the way, what I'm doing here is I'm fitting the resistance, elastance, inertance model, a single compartment model, to every simulated impedance. And I do that as a fraction of the maximal airway narrowing, and I'm looking in the black at resistance, all compared to normalized to baseline. The red and the blue are elastance and resonant frequency, which track together, and then the inertance actually, those three don't really change until we get up to very severe narrowing. What you see here is that the action's basically all in the resistance. So if you see a change in resistance like that, it's compatible with the idea that you're getting airway narrowing, and airway narrowing is always heterogeneous. If I do the converse and have random alveolar de-recruitment up to 80%, you can see now that it's the elastance that takes off predominantly. The inertance the elastance and the resonant frequency again track together, slowed down, and then the inertance is different. So we have different sorts of signatures based on a, reasonable, anatomically reasonable model of the entire lung. So the conclusions are the clinical usefulness of oscillometry may rely on the purely empirical use of those standard parameters, which you've heard a lot about. And listening to the talks today, I'm getting the impression that that's mostly what's happening and probably is what's going to happen for the foreseeable future. But if you really want to start saying, well, this parameter means that, and that parameter means this, and talk about small airways disease, peripheral versus central, that's where I start to get a little concerned, because the evidence or the rationale for doing that is very equivocal in my mind. And a lot of it's based on the historical use of models, which are probably inappropriate. So we have to be very careful about doing that. Interpreting these parameters anyway in physiological terms requires some kind of a model. And I just showed you one where it's my best attempt at this point to be as physiologically accurate or anatomically accurate as possible. There's no single correct best model, unfortunately. The standard parameters or the physiological interpretation of them that gets bandied about is based on that two-compartment model, which has its origins back in the midst of time when iOS was originally getting put on the map. And Monte Carlo experiments with an anatomically based model show characteristically different behaviors of impedance if you have developing heterogeneity of airway narrowing versus increasing alveolar derecruitment. I think that's it. Yeah. Thank you.
Hit the remind me later button on the remote. Look at your screen. Remind me later. Hit that.
Remind me later.
Yeah.
Oh.
Still die there. Yeah, just not at all. Yeah.
This one here. Yeah, right.
Jason, as always, amazing talk, very clear. My question is, when we use the term ventilation heterogeneity, does it therefore correspond to both the airway narrowing heterogeneity and the alveolar recruitment, would you say?
Well, you can get heterogeneity in both cases. Even with you get more severe heterogeneity with the diffuse derecruitment. But because the lung is heterogeneous, because the lung is asymmetric, so in other words, the pathway length down to any alveolus isn't always the same, you have an inbuilt heterogeneity in there as well. And you can make it worse by having this diffuse derecruitment.
So really, really neat. So it sort of, we dabbled a little bit of this with Swati, of course, and Del Leary made models
right.
and constricted airways at different generations. So not a Monte Carlo approach, but mimic the airway as much as best we could. Yeah. And in Swati's case, randomly narrowed airways in a given generation. Tried, I think it was from 9 to 11, right? And it was enough if you narrowed it to 75% or 90%, you didn't need 100% narrowing to get huge changes in elasticity.
Right.
And start to get the frequency dependence of resistance. But it mimicked more your elastic model. In other words, the elasticity was dominating the effect if she was restricting it. The thing was, she was limited to doing changes that were physiologically realistic. So she wasn't narrowing half of the lung. She's only narrowing the amount of lung that corresponded to, at the time, her images of ventilation heterogeneity. And Del Leary later on actually narrowed the airways that were feeding the defects from imaging and found the very same thing. It fell apart if you started to narrow larger airways further up the tree, because then the resistance started to dominate rather than the elastic. So what I think, I would really encourage you to try to, instead of randomly narrow airways with a tree or randomly do alveolar derecruitment alone, narrow the small airways, because we think that we're seeing small airways disease with reactants. And I don't know that you've convinced us, well, not me anyway, I'll just be me. Haven't convinced me entirely that it's alveolar derecruitment when we happen to see reactants going so negative. I think we can still get essentially derecruitment of alveoli if we do terminal airways just in front or a couple generations back, which are really not contributing a lot as long as you're not narrowing too much to the resistance.
Yeah, point well taken. I will do more of that. Actually, something I didn't tell you was, when I did the derecruitment, I didn't actually collapse the alveoli. What I did was I narrowed the feeding terminal bronchiole.
Okay.
So I kind of did what you just said in a
Should have said that.
way. But sitting more.
So Jason, in your modeling, you did either airway narrowing or de-recruitment. And in the disease alone both happen. So if you were to combine the two, I could see situations where you'd really tune up the gain of the response. If you tried that.
I haven't tried it with this. One thing I have done is taken that same model and allowed about 4 of those parameters to be the ones that determine narrowing to be free floating and actually fit it to impedance data. And from that, you can get sort of the rate of narrowing as you go down the airway tree, the amount of narrowing of the trachea. And you can, with a little jiggery-pokery, kind of infer what the degree of de-recruitment might be. So you can kind of get at it a little bit directly from the data set. Here I was just trying to sort of look at general signatures, but there's more that I can do. You're quite right.
When in your model, they take the from airway or first generation 25. What happen if you narrow it only generation 20 to 25 or 18 to 25? Or
Yeah, I mean, I can easily do that. I haven't done it yet, but a more exhaustive investigation.
If you could, I mean, my point is, can we measure those difference on those small airways versus the fact of the central airways?
Identifying that uniquely just from impedance of the mouth, I guess it's not. But I will say that, my thinking about this is colored to a certain extent to a large extent by work I've done on mice, a lot of it in the generation of Charlie and Leonard, where we found that with allergically inflamed mice, a major part of the physiology clearly is closure, because if you give the mice a sigh after following Brockman instructions, it's popular. And we saw these same kinds of signals.
Okay, so in order to keep on time, we'll go on to the
Charlie?
next talk. Yeah.
Zoli has a question, so we should.
No, he can't.
Yeah, Zoli.
Better be quick.
Go ahead, Zoli.
Hi, Zolly.
Hey,
Thank you, Jason, for this very, very provoking and interesting talk, and also for the fact that I can happily throw out half of my slides tomorrow because they become irrelevant. What was probably most challenging for me in your present talk is the contrasting of the heterogeneous and random closure of or shrinking of the lung units. And I was thinking about what is the real situation, and since I'm biased by the interpret changes showing that at end expiration and inspiration, very, very different impedances can be measured in the same subjects. So within one breath, that makes me think that if we have sort of recruitments and the recruitment during normal breathing, which may happen very easily in a diseased condition, then you must assume some preferential pathways which are active in recruitment and recruitment, which is probably closer to the heterogeneous approach to the random. What do you think about that?
Well, if I understand it, you're pointing out that there's likely to be inter-breath recruitment. Yeah, I completely agree, depending on the preparation. But what were you saying that you think it's? Oh, sorry. You think it's closer to the heterogeneous? I mean, the inter-breath recruitment is closer to the heterogeneous. Maybe I didn't quite understand that.
Yes, I might favor the heterogeneous model because if these changes take place not from one physiological condition to another, but within the same breath in a diseased respiratory system, then there must be preferential pathways which are probably less vulnerable to cyclic closure and recruitment.
Oh, I see what you're saying. Yeah, I see what you're saying now. Yeah, that's an interesting point. I hadn't thought of that. I could actually build that into this model. I haven't done that yet, but that's a good point. Yeah.
Thanks.
So
Tom.
yeah.
All right, our next presentation is, Joyce, are you getting?
No, Murphy's.
Murphy is,
Yes.
Murph the Sir. And we're talking about tale of two oscillometers. It's the best of oscillometers. You ready to go? Who's gonna help her get that?
I think she's a physicist. She should.
Oh, she can.
Excellent. Doctor's student or something.
And do you want this one? And we got that one. No, we might not do. Are we sharing the right one there? Just a little, yeah.
Yes.
And I stop sharing and we go to share screen again. And do we have the right one online, John Meyer?
Yes.
Okay. We'll accept this one here. Go ahead.
You just have to move slowly.
Let me just keep
Sorry.
slowly over the way here.
Don't wreck it.
I won't.
Don't screw it.
Oh, have we not maximized this? No, we have, okay.
It's focus.
Go ahead.
The screen.
Do the full screen.
Thank you very much for this opportunity to present. My name is Murphy. I'm an undergraduate physics student and a summer student in Dr. Chow's lab. And today I'll be talking about a comparison study between two oscillometry devices. I have nothing to disclose. Oscillometry, as I'm sure everyone knows, is a non-invasive and effort-independent pulmonary function test, which has shown potential for assessing lung function as well as detecting early signs of dysfunction. Commercially available devices have shown unresolved issues that have resulted in difference of outputs. So because of these unresolved issues, different devices yield different results. A study using mechanical test loads to test differences between devices found that there were significant differences among devices, especially at high impedance loads. A study done in pediatric population found that device-specific reference equations were necessary for the TremorFlow and the Resman device. And a study in an iOS versus FOT devices found that the iOS device recorded higher resistance, less negative reactance, and smaller area of reactance values than the TremorFlow device. The objective of our study is to compare the impedance measurements between the Resman Pro and the TremorFlow C100 device in a patient population with a wide range of lung function and abnormalities. Our patient population was made up of healthy volunteers as well as patient volunteers who were referred to the Toronto General Hospital PFT lab. Sequential oscillometry testing was done with both devices, followed by the regularly scheduled PFTs. And our statistical analysis was done using the Shapiro-Wilk test to determine normality, the Wilcoxon rank sum test or the pair T test to determine p-values, Bland-Altman plots to visualize agreement, intercorrelation coefficient, and the Spearman or Pearson correlation coefficient to determine agreement, Cohen's d effect size, and the Benjamin-Hochberg correction for multiple comparisons. Each of the participants in the study conducted regular PFTs after the oscillometry testing, and of the 76 total patients, 35 were classified with normal lung function with an average FEV1 over FVC of 78%. 26 participants were found to have restricted lung function with an average predicted TLC value of 67%. 9 participants were found to have obstructed lung function with an average FEV1 over FVC of 58%, and 5 patients were found to have mixed lung function with an average FEV1 over FVC of 61% and an average predicted TLC of 74%. For each device and each parameter of interest, the median and the interquartile range values were found. P-values were calculated between the devices to be less than 0.001 in all parameters of interest, indicating that there are statistically significant values found by each device. Bland Altman plots are generated with the Resman value subtract tremoflow value on the y-axis and the mean parameter value of devices on the x-axis. For the R5 parameter, the limits of agreement are shown in green, which are quite wide, and the bias is shown in blue, which is below 0, indicating that the Resman device finds lower values than the tremoflow device. After a mean R5 value of 4 centimeters H2O per liter per second, there's a downward trend away from 0, indicating that as resistance increases, the agreement between the devices decreases. For the R5 to 19 parameter, the bias is once again below 0, indicating the Resman device again finds lower values. After a mean R5 to 19 value of 1, there's a downward trend again away from 0, indicating that the agreement also declines after this point. The X5 parameter shows somewhat good agreement below a mean X5 value of -2. And after this point, there's trend away from 0. The bias for X5 is above 0, indicating that the Resman device finds higher values than the tremoflow device. In the area of reactance parameter, there's good agreement below an area of reactance of 10 centimeters H2O per liter. And after this point, the agreement declines between devices. The Bland-Altman plots were regenerated, taking into account the PFT classifications. And for the restrictive patients, the obstructive patients, as well as the mixed patients, there is no strict pattern present, indicating that it is not the type of disease that causes the disagreement in the devices, but it is the severity of the disease. When the normal lung function cohort is added, there is good agreement for most of these patients. In the X5 and AX parameters, once again, for the restrictive patients, the obstructive patients, and the mixed patients, there is not a pattern for these diseases, indicating that it's not the type of disease that causes the disagreement, but it's the severity of the disease. And once again, the normal lung function cohort shows good agreement for many of the participants. In the statistical analysis, the data was found to be not normally distributed, and p-values were found to be less than 0.001. The intercorrelation coefficient was found to be moderate to high in all parameters of interest, indicating that there's good agreement between the two devices. The Spearman correlation was found to be moderate to high as well, indicating that there's good monotonic agreement between the devices. Cohen's d effect size was found to be moderate to large in all parameters, with the negative values for R5, R5 to 19, FRES, and AX, indicating that the Resman device finds lower values than the tremoflow, and in X5, the Resman device finds higher values than the tremoflow. And because we are comparing multiple parameters, the Benjamini-Hochberg correction for false positives was made, and adjusted p-values were found to be below 0.001. We split the cohort of participants into normal lung function and abnormal lung function, which includes the restrictive, obstructive, and mixed patients. And the intercorrelation coefficient was calculated to be lower in the abnormal lung function cohort for the R5 to 19, FRES, and AX parameters. The Spearman or the Pearson correlation coefficient, depending on normality, was also calculated to be less in the abnormal lung function cohort. And Cohen's d effect size was found to be lower in the R5 parameter, the FRES parameter, and the AX parameter. And so our conclusions are that there are significant differences between the two devices. The tremoflow device finds higher resistance and lower reactance values, with a moderate to strong agreement found based on the intercorrelation coefficient, strong rank-based association based on the Spearman correlations, and moderate to large differences in measured values, particularly in the R5 and the AX parameters. There was slightly greater disagreement in individuals with abnormal lung function, particularly for the R5 to 19, the AX, and the FRES parameters. The abnormal cohort showed slightly lower intercorrelation coefficients and higher effect sizes, as well as decreased correlation coefficients in all parameters of interest. The differences could be from differences in hardware, signal generation, processing, or modeling, and our recommendation is that longitudinal monitoring of patients is done using the same device at all tests. I want to thank Dr. Chow for the opportunity to do this research, as well as Joyce Wu and the Chow Research Group for guidance and support. Thank you.
Good job. Excellent. Really was. You're standing up in front of this crowd. So I'm gonna ask the first question, if you don't mind. I know the people that develop both these devices. They're good engineers. And I know that there was extensive validation against physical models and wave tubes, and you did a bunch of that. And yet there's this profound difference when you start putting patients in the mix. So Murphy, we need to ask this guy, what's his opinion? What's his theory about why there's such a difference?
Okay, you put me on the spot.
Yeah.
Don't give it away. I want to discussion first.
We know the
Well,
answer.
okay, I'll start with, well, there was a study before that tested multiple devices.
Yeah, I can't remember who.
Yeah,
did that.
what idiot
This guy, and there were two devices that were in violent agreement over a fairly large range, over the test loads and patient, I believe.
We didn't do that. We didn't get the money to do.
You didn't do patient, that's right.
They're so messy.
Exactly. And it was these two, the Resmon and the.
That's right.
Doesn't opaquely say, or doesn't. It is opaque, actually.
Doesn't clearly say.
So, but I'll be transparent with those two. So I don't know, there could be differences. I think patients.
There are differences. Murphy found difference.
I know, okay. There could be reasons for the difference, let's say. The patients feel the devices differently, right? So Resmon is more of a energetic pulsing than the tremoflow. So that tells me there's a difference in amplitude. I'm not sure what's going on, right? Maybe the patients respond differently. I saw that there was agreement at low impedance, but disagreement at higher impedance. They calibrate differently. And so what usually isn't said in any of these talks is how you calibrate the device. What was your calibration test load used? So I guess that's my question. Did you guys use a 2 centimeter water per liter per second or the 15 centimeter water per liter per second test load prior to this study? And for both?
I'm
15.
Joyce.
Will answer that one.
Okay, 15 for both the Resmon and the tremoflow? Okay, so that's good. So that should have matched it at the higher impedance, except for one thing. It's the Resmon calibrates with the filter in place.
That's
right.
The Thermoflow does not. So it's very important you use the appropriate filter. I'm sorry.
We're calling you.
When you're using the Tremoflows, they sell the filters that you're supposed to use.
Very
Different.
expensive filters, I might add. Editorial.
So if you use a different filter at higher impedances, you'll start to see differences.
Are you buying this? You're a physicist.
Yeah.
Does this make sense?
Yes.
Okay. Okay, we buy it.
I wouldn't have expected such large differences for that reason, though.
Yeah.
So I don't know.
Do you use manufacturer recommended filters on your tremoflow?
We use the ones in the PFT labs that I'm using for this spirometry test.
But we switched. No, that wasn't. That was a couple years ago? Yeah. We can't afford the Doris's filters.
There we go.
I know.
There clearly were differences and there was a bias as well.
Yeah.
But can I ask you guys, were they significant? Because when you did your paper you published 5 years ago, where you comparing all the devices, even though they were in violent agreement, they weren't in perfect agreement. So were those differences big compared to the?
Yeah, those are
differences
big
we found?
difference. I mean,
Yeah.
the question is who's right? We had the wave tube to serve as our gold standard. So we were able to see those that deviated and both these devices tested here agreed with the wave tube at the time in a single compartment model. We tried to mimic breathing. So it was a human. I mean, ideally, we would have gotten a population of individuals because always the question was, well, will it be the same way? But lack of funding precluded us going on with that. And I think this project speaks, even though we may know what's going on, maybe the mouthpiece is giving you an upper airway shunt that's not accounted for because the volume of the mouthpiece used is not the one that's assumed to be there by thoracists. So that very well may be it, but that's a hypothesis. We'd have to go back and read the study with the appropriate pieces. And if it's not that, then surprise, surprise, people in models behave differently. Well, what else is new? And so then we would really need to do the study to compare, which would be an expensive one, of recruiting in real life patients across the spectrum of disease and acutes and compare them on all the devices, which now is not 5. I think we're probably up to 10, if not 12 commercial devices, if you count what's also in development. So it'd be a complex test to do.
All right,
But from a, yeah.
we've got some other questions here, guys.
We'll wait.
Oh, well, he's gonna have to wait.
I'm gonna ask a very naive question. But for this, in the beginning, we talked initially about the patient's reference, right? And what numbers we should use it. But with difference of the instruments, get hard. Shouldn't we step back and start to talk about instrument standards, and between different companies like a spirometry, CT scan, and people have to come to agreement on what are the minimal, requirements or
Good luck with that.
there should be.
Claire.
So I'm gonna assume that there's normative data for both these devices. So as a clinician, I really care, are you normal or not? So if you have normative data and you classify your patients for each device, how many are discordant classification? Because to me, the absolute number is less important as opposed to, where are you fitting? Are you normal or not?
You're thinking about it and you're gonna do it later.
So I'm not pretty sure of what.
Yeah.
Well,
it's a
if
very
there's
good-
normative
But the-
data.
You're gonna think about it, we're gonna do it later.
Okay,
Figure the answer.
okay. I'll accept that answer.
Okay, good.
I do.
Problem is
comment-
One more
Yeah,
question,
sorry.
comment and one
I
more
want-
question.
We were using the tremor flow filters for a long time when switched over to something a little bit more nice front. We did some comparisons with the longitude patients. We did not find a significant difference, which is why we decided to go ahead and do this.
But were those patients higher, low impedance and patients?
We can go back and.
You'd have to see, because if they would happen to be low impedance, you wouldn't see.
We would have to go back and, but these are a wide range of patients. The other thing is, I wanted to. I'm too, from the Resmond. Was commented from our patients. I have
What's-
somebody from our lab calls it the sputum induction. Because it was just so strong that she kept coughing after each maneuver. And she's a healthy,
Which device was that?
the Resmond.
All right, what does Hantos have to say?
Zoli, you're on.
Quick, short.
Unmute.
Sorry, congratulations, Murphy, for this study, which was nice, but at the same time, fairly disappointing. But we are in the direction of the disharmonization instead of getting the devices closer. I have one question, and depending on the answer, another one. First question. Did you use the same signal type in devices during the measurements? I mean, 5 to 37, almost all prime number signals. Yes.
Oh, sorry. Yes, we use the spectral 5 to 37 for tremor flow and the pseudo-random noise for the resonance.
What was it?
Which is basically the same,
No,
apart from
not
the
the
tremor
full-
noise.
It was the full spectrum. Full spectrum.
Okay, good. So this is very bad news because my suspicion was that if you had the three component with Resmon, that might be a signal amplitude dependence behind these very discordant findings. But in this case, apart from the different degree of sputum induction with the two devices, I have no answer for that.
All right, thanks.
Thank you very much.
Congratulations, Murphy. You did a super job. How many of us at that stage of our life would be willing to get up and give a talk like that? Really excellent job. All right, our next contestant, presenter, sorry, is Dan Genkin from Toronto, and he's talking about predicted baseline allograft dysfunction using quantitative CT and oscillometry.
Yep.
All right, man, take it away. I can't help you with getting.
No worries. I got it.
You got it?
Yeah, thanks.
Better.
All right. So thank you very much for the introduction. This is a collaboration between my supervisor, Dr. Miranda Kirby, who of course specializes in quantitative CT, and Dr. Chow's research group. And let's just jump right into things. So we know that survival after lung transplantation is very poor. If you look at this figure over here, looking at the 4 major solid organ groups, we see that survival after particularly lung transplantation is only around 25% after 10 years. And primarily what's driving this poor long-term mortality statistics is allograft failure. But we're not only interested in long-term allograft failure, we're also interested in early graft dysfunction. And cleverly, a group in 2018 coined baseline lung allograft dysfunction. So what you do is you look at the lung function FEV1% predicted post-lung transplant, and you quantify something known as the baseline or the peak lung function. And essentially, you ask yourself, did this peak or baseline surpass our normal threshold of 80% predicted? And this early allograft dysfunction or baseline dysfunction is fairly common, affecting roughly 40% of those receiving a lung transplant. But there's also particular interest because those that suffer this early graft dysfunction later have a quickened time to chronic decline in their lung function and allograft failure. They suffer from a reduced quality of life, and of course, they have impaired survival. But we do have known clinical risk factors for blood, particularly pre-transplant recipient factors that we know to be important. We have donor factors we know to be important, and we have perioperative factors just after surgery that we know to be important. But of course, in the hospital, clinical data is not the only piece of information from the bigger pie. And as a quantitative CT analysts, we of course rejoice that CTs are typically collected routinely 6 months post-lung transplant for us to analyze. And a little bit about CT. I know it's an oscillometry conference, but a little about CT. So what we do is we can segment the lungs, and you can see the lung border visualized there, and we can extract quantitative CT biomarkers describing lung size, for example, total lung volume analogous to TLC. Not really analogous, but that's okay. That's a conversation for later. We can evaluate the density histogram of the segmented lungs and evaluate its mean position to extract mean lung density metrics. We can segment the airways, which is much harder to do than the lungs, but nevertheless, we can do it. And we can focus in on specific generations of airways, for example, the segmental airways. And then we can look at cross sections to look at lumen areas. So how big is your lumen? We can look at the wall size relative to the lumen to extract wall area percent metrics. And typically, again, we focus on the segmental airways. And finally, of course, we can also segment the pulmonary vasculature, probably the hardest structure to segment, but we can still do it in order to focus on pulmonary vascular volumes, typically in milliliters, or the proportion that is made up by the small vessels less than 5 millimeters in cross section. Back to oscillometry. So oscillometry in blood is very limited. There's a single study published in 2023 by Darley. And essentially what they found was that those that have blood have elevated resistance and decreased reactance relative to those that don't have blood. And interestingly enough, this was also the only study to look at qualitative CT. So CT findings in general. So they found increased rates of pleural thickening in those with blood. But there are several limitations with this study. First and foremost, the measurements were not time matched between the two groups. But secondly, as to my previous slide, they only evaluated qualitative radiological CT findings, none of our objective quantitative CT metrics. And finally, they never studied the interplay between our oscillometry functional measures and our structural QCT measurements to see if they provide synergistic information. So that, of course, led us to a research question, which was, does our functional oscillometry data that we can collect and our structural QCT data, do they provide complementary physiological information beyond the clinical risk factors that we talked about earlier for understanding and predicting who will develop blood, essentially? And our specific objectives were to, 1, investigate correlations between our structure and function. 2, using our 3 feature sets, identify what feature set was the most optimal for predicting blood. And 3, finally, from this, using machine learning, and finally, from this most optimal combination, what were the most important features selected? So to do this, Dr. Chow's group partnered with us, and we investigated bilateral lung transplant recipients from Toronto General Hospital under the lung transplant program who received 6-month oscillometry and CT post-operation and had to have survived to at least 12 months because we needed to retroactively go back and evaluate if they did or did not have blood. So we analyzed the data from these patients and, of course, included the known clinical risk factors like the recipient factors, the donor factors, and the perioperative factors, all guided by literature. At that 6-month time point, the Chow research group at Toronto General extracted spectral oscillometry with, you guys are experts in this, so the common R5, difference between R5 and 19, X5 and AX, but they also extracted intra-breath oscillometry, so the end inspiration and end expiration counterparts to these measurements. Then over at our TMU location, we used a commercial software known as Vita to automatically segment the lung parenchyma tissue and extract our known QCT biomarkers describing lung size, lung density. There's some other metrics that are important in CLAD literature, so long-term outcomes, in COPD literature. So this is all guided by literature. We automatically segmented the airways and obtained QCTs describing airway morphology. So how many airways do you have? How big is the lumen? How thick is your wall relative to your lumen, etc. And finally, of course, the pulmonary vasculature was segmented. We obtained a measure of the complete pulmonary vessel volume and the proportion made up of the small vessels. So at that 12-month time point, we can then go back, retroactively look at their lung function, and assign a blood status. Once we had this binary blood outcome, of course, it's an easy machine learning problem. So essentially what we did was trained a random forest classifier using L2 regularization because a lot of the features were highly correlated, so you have to control for that. We split our data 50-50 into training and testing because we had a small sample size. And we also evaluated all possible combinations of feature sets, including just clinical data alone, including oscillometry, including QCT, and the combination of all 3. We evaluated model performance using the AUC curve, fairly standard machine learning performance, and investigated differences using the Long's test for statistically significant improvements in performance. And finally, we investigated the most important features using a SHAP analysis from the most optimally performing model. So patient selection, we had around 99 patients in this study, roughly equally split between no blood and blood. And then we split them 50-50 into development and testing. And we further split development into 2 folds for cross-validation to optimize the hyperparameters. Now notice that at each point in development, testing, training, validation, we have equal splits of no blood and blood relative to the initial set. In terms of the clinical characteristics, the 2 groups are very well matched in terms of age and sex. But the blood patients did have a greater proportion of ILD as their transplant indication. Surprisingly, the donor characteristics were well matched. But in terms of their perioperative recovery, we saw that blood patients had smaller SpO2 FiO2 ratios, and a longer amount of time spent intubated relative to the no blood group. All right, so you guys are probably interested in this, correlations between structure and function. So we're gonna take it slow here, starting with R5. We're gonna run through correlation coefficients with lung size, TLV, lung density, MLD, lumen size, LA, and wall size, wall area %. So R5 was only significantly correlated with lumen area. So what we saw was, as lumen area increased, resistance at 5 Hertz decreased significantly. In terms of R5 minus R19, we did not see any significant correlations. But for reactance at 5 Hertz, we saw a significant positive correlation, meaning that as lung volume increased, reactance also increased significantly. Similarly with AX, just in the opposite direction, because obviously the measurements are flipped in sign. But when it gets interesting is when we add the intra-breath components to it. So looking at end inspiration and end expiration correlations, we now see that resistance is, again, still correlated with lumen size, but now also correlated with lung size. So again, both larger lumens and larger lungs decrease resistance at both breath phases. And then when we look at reactance, we now see mean lung density be a player as well. So increased reactance at both inspiration and expiration was correlated with bigger lungs, and a higher density in the lungs was correlated with a decreased reactance. So to summarize, essentially, smaller lumens increased resistance. I think you guys made it clear from the seminar. That makes sense. And then smaller and more dense or stiffer lungs, we saw decreased reactance. Machine learning model performance. So again, these results are fairly easy to follow. So we saw clinical performance was fairly poor, just using the clinical data at 0.64 to discern blood status. When we added oscillometry to the clinical data, performance improved, but this difference was not significant, although performance was better. Just the clinical and QCT, performance was significantly better than just the clinical data alone at 0.77. But to no one's surprise, when we combined all three together, our structure, function, and clinical information, performance was the best on our test set with an AUC of 0.81, which was better than just the clinical data alone and the clinical and oscillometry data alone. So the way we summarized this was that the three feature sets, when combined, optimize machine learning model performance. Now, you might ask, what's driving this optimal performance when we combine all three feature sets? And that's what the SHAP analysis does. So for those that have never read a SHAP graph, the way you read this is values on the right are predictive of blood. A pink color is a high value and a blue color is a low value. So the most predictive feature of blood was the large amount of time spent intubated. And then as we move down, it's second most predictive and so on. So a higher CT mean lung density was predictive of blood, a lower end inspiratory reactance, a lower kurtosis, meaning a flattening of the lung density histogram distribution and a shift towards higher density values, and a lower SpO2 FiO2 ratio. And what you see here, it's really a beautiful mix between two clinical features, two CT features, and an oscillometry-based feature. So the interplay between clinical data, structure, and function is really coming to play here. And the way we summarize this was worse transplant recovery, increased lung density, and decreased reactance were most important for predicting who will develop blood. So key takeaways from the presentation. There were correlations between our structural QCT and functional oscillometry measurements. Intra-breath oscillometry showed stronger correlations than spectral oscillometry. And finally, to no one's surprise, when you incorporate all the possible patient information from structure, function, clinical data, we see a synergistic enhancement between the feature sets for performance to predict the lung transplant patients that will develop blood at 12 months. So for you clinicians, how would you potentially apply such a machine learning model in clinic? This is where it kind of gets murky, but this is our attempt to kind of see what's going on and how we can apply it. So let's say you have a 57-year-old male who undergoes a lung transplant, and let's say you have a 59-year-old male who undergoes a lung transplant. According to the model, we focus on the clinical features that were most predictive of who will develop blood. And the two patients have their lung function tracked post-lung transplant up until that 6-month time point. But as you can see, there's no clear discernment with that 80% normal mark for if someone's going to cross it or not cross it. at which point we collect our oscillometry and focus on the feature that the model deems important, and our CT and focus on the features that the model deemed important. And what our model can do is assign a risk score, essentially. So, you know, one patient has an 85% risk score for developing BLAD at 12 months, and the other one has a 23% chance. And what we can do is, you know, the disease is in its very early form of characterization. And when we know who's at high risk of BLAD, we may be able to focus our characterization on those patients and really enhance prognostication for the disease. But yeah, welcome, please, any comments, and thank you, Dr. Chow, for allowing me to present this work here, and open to any ideas. So thank you.
Dan, what are you? A student or resident?
I am a fourth year PhD candidate under biomedical engineering.
Okay,
Yep.
great. Good, because you didn't put any of the clinicians out of business, so that was good. And Dave,
What is the histopathology of BLAD? What compartments of the lung are affected? Is it the alveolar epithelium, vasculature? Tell us more about that.
Good question. I'll take a stab at this. So I know there's not much known. It was coined in 2018. It's you know, could be similar to like a clad restricted, but we don't know. Essentially, there's no phenotypes. So unlike clad, are you familiar with clad?
Yeah, I mean, basically, I'm trying to get at, mostly you're finding parenchymal changes.
Yeah.
So it would suggest there are parenchymal defects structurally in BLAD.
there must be pathology.
Yeah, I'm, because it's not fair.
You
to
gotta
ask-
bail
It's
them
not
out.
fair to ask.
Okay, that's.
Sure it is.
PhD candidate, but no one really understands what you're glad to be. And there's very, very little physiology. These are not patients who will undergo transplantation, and they'll be like the only way.
They must get by it.
They get biopsies, but these are transplanted biopsies, which really only look at basically. So, but the underlying sort of thinking is that this probably process that is.
So what?
Multi-factor, but there's and I think a huge component of it, and the reason why patients with IOD at a highest risk of developing BLAD is probably chest wall, chest cavity mismatch, because at time of donate of transplants, the lungs are matched for size on the basis of predicted values, not on the actual size in the chest wall. So it's a predicted value of the recipient, not their actual. Right, and it's the predicted size of the donor, because most donors don't have actually breast.
Maybe that's why pleural thickening was associated on the qualitative. perhaps?
Yeah.
So is there an acute inflammatory process, or is it more like persistent atelectasis?
I think it's probably consistent with atelectasis, to be honest, like histology, not other than transplantation violence.
So what's the treatment?
And so that's why I think that that one study with oscillometry, that really is like a restricted pattern.
Yeah.
Right.
Increase AX, decrease X5.
Right.
What's the treatment? What do you treat these folks?
There is no treatment other than sort of, a sort of prevention of any bad things happening, so increase in monitoring.
No, that I get, but I mean, once they start to, there's no.
There's no treatment.
Okay.
There is probably some patients respond better to azithromycin to decrease some of the infections on that, but also that's also not clear, because then you have patients respond better, but doesn't affect them much in terms of the survival of those patients.
But if you split your population into really pulmonary fibrosis versus interstitial, which very often are, connective tissue disorders, so they have chest wall, just restricted to pulmonary fibrosis, you will see the same. I mean, I think it's fabulous, but it's just, these populations with mixed connective tissue disease who have interstitial lung disease, you put in new lungs, but the rest of them are still connected.
Still correct.
I saw some of the pathology data of BLAD, which they show like a lot of mucus hypersecretion earlier. Is any the reason why they able to divide between those that actually sprint muco-obstructive.
Yeah, I mean, the blood patients are sort of at higher risk for bad stuff. Right? So they tend to have more infections. And they like the worse sort of your baseline function, the higher the risk of developing blood. But it's just that you've got to lower.
Well,
So
their immune
baseline to start
system is
off.
likely very poor.
Well, one thing I wonder about is that some people have shown that if you have really persistent anaphylactosis, I mean, not like weeks to months, you can actually, I think it's called alveolar induration. You actually lose alveoli, kind of get stuck together and then get absorbed or something.
I'm sorry.
But that could be this next project.
Nice study.
Thank you very much.
Appreciate it. Thanks.
guys.
All right, our last presentation before coffee. So McGill, there you are. We thought we'd lost you there earlier. And you're going to tell us about some more machine learning, predicting lung function using spectral oscillometry. We're all excited.
Thank you. All right, good afternoon, everyone. My name is Sayed. I'm a research associate.
Louder.
Okay. I'm a research associate working in MUHC. We work with Dr. Brian Ross. He's now in the service. That's why he couldn't join us today. But from morning, we have a lot of nice talk, and we saw how oscillometry is powerful and sensitive. Now, the purpose of my presentation is to show you even we can make oscillometry stronger when we combine it with the machine learning and those kind of stuff. So in the next couple of minutes, I would show you how we can use the machine learning to basically predict the gas trapping and hyperinflation that only can gather by a full PFT. So when we talk about the COPD is the third leading cause of mortality, and unfortunately has a prevalence of more than 10%. PFT is the gold standard for assessing the lung function. And as a part of full PFT, we have the plasmography, which is used for gathering the information related to the hyperinflation and gas trapping. Performing PFT is quite challenging for a patient with the severe COPD, and also is the infrastructure needed. Means we cannot do it everywhere, anytime. No surprise, on the other hand side, we have oscillometry, non-invasive, and can provide some information about the lung mechanic. So if we look at the literature, we can see that the number of the published paper on the oscillometry is exponentially increasing. Means oscillometry is receiving a lot of attention in the research community. So the objective of this study was to see, can we kind of replace this plasmography by using the data that we gather from the oscillometry and empower it by machine learning. So we used the data from the observational study involving adult with the GOLD 1 and GOLD 4. In the oscillometry parameter, we just gathered those general parameters, resistance at the two different frequencies, reactance, and AX. And each participant also, they went under PFT, and we gathered the total lung capacity, TLC, and the ratio of residual volume to TLC. As I said, hyperinflation and gas trapping basically can determine by these two parameters, TLC and the ratio of the residual volume over the TLC. We developed very general machine learning model, CNN, and the purpose was to predict the TLC and the ratio of the RV-TLC. The machine learning had the 10 input, very simple model with 2 hidden layers and output of 2. Inclusion criteria was to basically choose the very severe and mild patient. This is the result that I have here. In total, we had 17 patients. And when we look here, there is an even distribution between the severity of the disease, GOLD 1 and GOLD 4. And once we talk about the machine learning, bias is very important. And to minimize the bias in this study, what is the noticeable also, you can see that the distribution between the male and female are even. So I call those part equal distribution between the severity of the disease, and male and female is the strong part of this study. So we divide the data for the training and validation with the standard ratio of the 80 to 20, and we kind of run the model initially. What we got was not that much good. The accuracy was unfortunately 60%, but we optimized the model with the general method that very known in the computer science part. It's called cross-validation. We did it. We did not see a huge improvement in accuracy of predicting TLC and RV-TLC. So what we did, we incorporate the other demographic data of the patient, like age, BMI, sex, and smoking history and the severity of the disease, which is GOLD 1 and GOLD 4. What we saw as the accuracy in predicting TLC is increased to the 92%, and the RV-TLC 88%. So as a quick conclusion, I show you that yes, we can use the oscillometry data and train the model to kind of tell us some information about the gas trapping and hyperinflation. Of course, this study has several fundamental, I can say, fundamental limitation, and one is the limited data set. And just at this study, we focus on the GOLD 1 and GOLD 4. We kind of ignore the GOLD 2 and 3. So as a future work, we would test this approach for a bigger data set. And here we just developed very general ML model, which is known that is not very super performing. So once we have a bigger data set, we have this freedom that we can go to the more advanced model. So thank you for listening, and I'm open to answer.
Peter? Where's Peter? What are you doing over there, Peter? We're calling on you. Who's Peter? Raise your hand. We have a Peter.
Peter Savaji, are you here?
I'm Peter, but
There you are.
I didn't think you were looking for me.
It's over there.
I lied.
Well, that's not the first time you lied. Peter, any thoughts? He told me to ask you, so don't
I
blame
wanted to
me.
see if you were paying attention.
Only partially, to be honest.
Well, I wanted to know what you thought of machine learning with 17 subjects.
Yeah. It's tough, but also depends on the dimensionality of the data, but yes, the subject is not much for sure.
Yeah.
But it's good preliminary data.
More is better.
Yeah.
Yeah.
But
So
Did you sample, resample? I mean, how did you get over that limitation? Or were you just saying that the oscillometry coming out of each patient is so vast that I have enough data?
First thing that I did, I developed a model that works with the low data set. And also, what I implement was that to avoid the overfitting was to implement some sort of algorithm that doesn't let model keep training and keep training. So that was kind of strategy that I used for these 17 patients, but still I accept that, criticize that it's a very limited data set for the machine learning.
But you're gonna get more data.
Yeah, we have sorts of.
So you added 5 more things to improve the accuracy, age, BMI, sex, smoking, and one other one that I know.
Right.
Did you do that stepwise or?
Yes, we did the stepwise, and one of the very critical parameter was the sex plus BMI. These two was, yes, mandatory.
Yes, sex is always mandatory. Well, it's true, right? I mean, it's a major determinant of a lot of things. It's certainly size and height. Jason?
I'm wondering why you didn't have height in that list, because height is classically.
Yeah.
Right.
Supposed to lung size. And as
you
as
try?
regards the limited number of patients, well, as Charlie said, you're gonna get more. It's a good start. But the more fundamental question I have is, why are you interested in lung trapping and lung science? Because when you're studying COPD patients.
Right.
As I understand it, you measure those things in order to figure out how sick they are.
Right.
Why don't you just go straight from oscillometry to how sick they are? Why are you taking this intermediate route through?
So in order to get gas trapping and the TLC, what we do, we put the patient in the box for the plethysmography.
No, I get that. But you do that in order to figure out what their goal state is, right? Predominantly?
No,
No,
because
no, gold
I-
Why do you do that? Why are you interested? Some of the clinicians tell me, why do you care about
Because
lung volume?
pseudo normalizations, people won't qualify for the COPD diagnosis despite having it because there's an elevation of the RV that decreases the F. So the ratio is normalized only by putting them in the box currently and measuring their TLC. And you figure that out and say, oh, you have COPD and pseudo normalize your ratio because look at all that gas trapping you have.
So you measure lung volume and gas trapping in order to make a diagnosis of COPD.
Yes,
Why don't you go straight from oscillometry to a diagnosis of COPD?
what, based on
Using machine learning.
well, that's the point of this thing. This is.
No, but he's going to
Oh, I
lung volume
see.
and gas trapping. I'm saying, why do you care?
Yeah, well,
You
maybe,
go straight to the-
yes, maybe,
Yeah.
maybe we do. So there's another summer project.
Well,
So let's ask,
we've done.
answer Jason's first
Oh, it doesn't
question.
work, okay.
Height, what about standing height?
Yeah, we didn't include the height, but the absolute.
Oh, you should go back and do
Yeah,
that, because he's dead right about
Yeah,
that.
no, correct, because for the PFT also we collect the
Yeah.
height.
But Sean had the answer to this question.
Oh,
Yeah.
she
So,
did.
yeah, it doesn't work. So we've tried, we've never heard about this because it's a negative study. So we tried machine learning with, I can't remember, several hundred patients who had normal standard PFTs, right? So normal obstructive, it doesn't work. It's got an accuracy of like
In order to diagnose.
in order to even separate the two. So
But with
he's-
oscillometry, with
with
oscillometry,
oscillometry.
you can't do it with oscillometry.
can't do it with.
And yet with oscillometry, you can get diagnosed worthy values of lung volume and gas trapping. Which means that the information is in the impedance to give you gas trapping and lung volume, which contains the information to tell you whether they have COPD.
But that's only in a population that is already selected with COPD, right? So like your
Yeah.
question was, why don't you just go from oscillometry directly and say this patient has COPD?
Yeah.
But that's only because that population has COPD. Right, because
Correct.
you don't have it, you
Correct.
don't have any healthy.
Right, correct.
Okay, so then my question is, why are you measuring lung volume,
So that's.
gas trapping?
That's a question.
Yeah.
Apart from the fact that it's interesting. I give you that.
But that's the question I asked. To save the patient being tortured in the body box.
But if you measure oscillometry, you go straight to the diagnosis, they're not tortured.
Well, we have to do that study. We don't know that. I mean, presumably you're right, the information's there, but we have to learn how to attract it. We can't have it on blind faith, right? We have to
I
show it.
think I'm wrestling with the transitory, which is if A equals B and B equals C, then A equals C.
I know. But we are clinicians. We have to see it.
Okay.
Conditions are not bothered with. Don't worry about it.
Yeah.
All right, Jeff.
Perhaps a
Last
difficult question is you've shown that if I add BMI, age, sex, and smoking, maybe one other, but not yet. That you improve your estimate that you had, which was a 60% estimate with oscillometry alone. You haven't shown us how well those do without oscillometry. Would be, if I'm asking, do I need oscillometry? If it actually adds benefits, I want to see that.
I don't know the answer, but it's interesting to do a.
Well, certainly smoking if it's heavy enough.
Yeah, absolutely. You know that.
Oh, well, thank you very much.
Thanks.
And we're ready for coffee.
So welcome back, everyone. Just give everyone 10 seconds to sit down, Ron. So it's a pleasure to welcome Robert Dubé. We a little bit switch in pace. I think many of us hear about respiratory oscillometry in the obstructive lung disease world, and there are a select few who are interested in oscillometry and interstitial lung diseases. So Robert, without further ado.
Hello. Open up my presentation. Do my best, guys. Is it working?
Yep.
Yeah.
Perfect. You're good.
All right. So hello, everyone. My name is Rob. I'm a third-year resident in internal medicine, and today I'm going to be discussing a project that I've been involved with for the past year and a half or so, titled Airwave Oscillometry as a tool for monitoring disease progression in interstitial lung disease. So first off, here are my disclosures. So interstitial lung disease, big change. Everything else has been obstructive, but for anyone who doesn't know, it's a heterogeneous group of diseases characterized by inflammation and fibrosis. These conditions carry a very poor prognosis with relatively high one-year all-cause mortality rates in studies. And they're also characterized by disease progression as a natural course of the disease. In one study, again, about 40% progression after 2 years. The main management strategy in these conditions, unfortunately, is not reversing the disease, but preventing disease progression. And while it'd be much better to be able to reverse disease, this strategy has shown to be fairly effective, with 5-year mortality rates amongst patients who did not progress of only 9%, as opposed to about 40 or more in patients with progressive pulmonary fibrosis. Disease progression is characterized on the basis of worsening respiratory symptoms in the presence of physiologic and radiologic changes associated with progression. And in day-to-day clinical practice, the main tool that's used for monitoring disease progression is spirometry, and namely measurement of the forced vital capacity, or FVC. Now, while spirometry is very widely used and established to be quite reliable, it is a cumbersome test. It's complicated. Patients need to be able to actually perform forced exhalatory maneuvers. And this can be very difficult for patients who have severe interstitial lung disease. I remember talking to one patient in particular who told me that he dreads going to see his respirologist every year because he's worried he won't be able to perform the tests and he'll have to keep trying and keep failing. So in these situations, an alternative would be worthwhile, and oscillometry, as you all know, requires only passive tidal breathing. It doesn't have as many contraindications, and according to some patients, seems to be easier to use. Now, while we've heard a lot about obstructive disease over the course of the day, there is some research, though much less related to interstitial disease. I believe in our opening presentation, if I remember correctly, there were 47 publications as opposed to about 1,000 on asthma and COPD. What is known is, from a clinical perspective, there are some characteristic changes one would expect. So sometimes an increase in R5, but more consistently an increase in AX, resonant frequency as well, and a decrease in X5. Based on the available literature, these seem to be relatively well correlated with both FEV1 and FVC, decreasing
as these changes occur. And there seems to be some degree of clinical correlation as well, namely a reduced survival at 3 years when these changes are present, and a greater functional impairment as the changes get more and more extreme. From a technical perspective, what we have shown just recently, another group from, I believe, the UK, has shown that repeated measurement of oscillometry in patients with ILD is reproducible on short-term repeats about 2 weeks apart in patients with stable disease. So that would suggest that if you have stable oscillometry values, you can be fairly confident that you have maybe a stable disease status or at least stable FEV1 and FVC. That's encouraging for the eventual adoption of oscillometry as a tool for monitoring ILD. But it's unfortunate to see that this is only now appearing when oscillometry has been around for multiple decades at this point. So there's really a lot of work to be done. One thing I noticed when looking over the literature is that in ILD, there's very little prospective longitudinal data. Some studies look at patients at multiple time points with repeated measurement of oscillometry, but it's very few. Now we know physiologically spirometry values do decrease with age, and there are a number of different parameters that are also impacting the values you receive. So if we want to make this an effective tool for monitoring disease status, we need to be sure that we can confidently rely on the values that we see when it comes to a longer duration of follow-up. So in simple terms, the question we were asking was basically whether or not time and the passage of time simply in an otherwise stable patient would confound the previously established relationships between spirometry and oscillometry. So in order to do this, we conducted, we had two main objectives. The first was to evaluate this relationship between oscillometry and spirometry in interstitial lung disease over time. And secondly, to determine whether or not changes in oscillometry are sensitive to changes in ILD. So to do this, we conducted a prospective longitudinal cohort study, and we included participants over the age of 18 with a diagnosis of ILD from any cause. At study enrollment, patients provided us with demographic information and information on baseline symptom severity. We conducted spirometry and oscillometry at the time of enrollment. Then patients continued to receive standard of care management as per the recommendations of their treating respirologist for a minimum interval of at least 6 months. And then they went through a follow-up evaluation where we did repeated spirometry and oscillometry. After this, we also conducted a chart review looking at the study interval for evidence of symptomatic worsening, changes on imaging suggestive of disease progression, and finally, physician decision to initiate additional lines of therapy for these patients. We conducted statistical analysis using Spearman correlation at each time point to look for correlation and the persistence of that correlation. We then conducted a linear mixed effects modeling analysis to evaluate whether or not there was a time dependence in the relationship between spirometry and oscillometry. And finally, we attempted to correlate the changes that we were seeing clinically using the chart review data and analyzing with repeated measures ANOVA. So in total, we were able to enroll 43 participants, and of these 43, only one was lost to follow-up. The remainder completed the entirety of the study. We had a median follow-up period of 384 days, and the cohort was nice in that it was relatively well distributed according to gender and smoking status, and a variety of different ILD diagnoses were included, most notably IPF and SART-ILD. However, there were a number of others as well present in the cohort. So here's our baseline parameters. We looked at FEV1 and FVC and the ratio between FEV1 and FVC in all participants. If data was available as per clinical need, DLCO was also collected and analyzed. And for oscillometry, we looked at R5, AX, the resonant frequency, and X5. The majority of our patients had a purely restrictive spirometry profile. However, 5 subjects also had a concomitant obstructive defect with a FEV1 to FVC ratio of 0.62 on average. What we noticed very early on is that the oscillometry parameters are not normally distributed, as can be seen. There's multiple outliers, and it almost, a lot of these parameters almost present with a log normal sort of distribution. So we transformed the data using a Box-Cox transformation, which resulted in the data becoming normally distributed. Looking onto our analysis, we conducted Spearman correlation first, comparing FVC with all of the different oscillometry parameters. And what we saw was that there was a moderate to strong correlation between FVC and all of the parameters. So if we look at the panels here on the side, the dashed blue line and the triangles represent baseline data points, and the orange line and the squares represent follow-up data. And in all cases, there's a substantial overlap with the trend lines and the data points themselves. In some cases, particularly for AX and FRES, the trend lines are almost identical. So parameters remained well correlated over time at both the baseline and at follow-up. And more interestingly, there was no difference in Spearman correlation coefficients when compared between time points. So the conclusion we drew from this is that there is a persistent correlation. There are persistent correlations present on single time point measurement of FVC and different oscillometry parameters. Similarly, we found essentially the same relationships present in FEV1. So again, here looking at the figures, very similar trend lines in all cases. And again, the Spearman correlation coefficients remained very similar with no statistically significant difference. We also conducted the same analyses, trying to find correlations with FEV1 to FVC ratio and DLCO. The FEV1 to FVC ratio did not show any real correlation. And DLCO, while there was a trend towards a correlation, it did not meet significance throughout for the different parameters. Part of the reason for this is because DLCO data was not consistently available, as we only collected it if it was deemed necessary by the treating physician. So the statistical power may have been a little bit lower. From there, we conducted a linear mixed modeling analysis. The model allowed for a main effect of the spirometry, the oscillometry parameter in question, time, and the interaction between time and that oscillometry parameter to look for whether or not the relationship between these parameters remained constant, even despite the passage of time on long-term repeat measurements. What we found was a significant relationship between FVC and both AX and FRES, as you can see here in bold, in our unadjusted model. And when we adjusted the data set to account for age, sex, height, ethnicity, and smoking status, all of which could potentially impact FVC, we found that these relationships remain significant. Perhaps even more interesting, there was no significant interaction between time and the oscillometry parameters, and no significant effect of time, which suggests that the relationship we're seeing between FVC and oscillometry and the oscillometry parameters is not influenced by time as a potential confounder. And that's important for long-term follow-up and monitoring using this technology. From there, we attempted to correlate this clinically. So first off, we looked at symptom severity. We stratified our cohorts by interval symptomatic worsening over the course of the study. And what we saw, as expected, in patients with worsening disease status, there was a decrease in FVC with symptomatic worsening. There was also a decrease in X5 and an increase in AX in patients with symptomatic worsening, which is consistent with previously published studies in this population. So looking at the figures here, the blue dotted line is patients who had stable symptoms, and the orange line look for patients whose disease status worsened in some way. We then tried to do a similar sort of analysis looking at changes on imaging. Here, unfortunately, there was no real significant patterns that we saw. A possible explanation for this could be that maybe symptoms appear much earlier on in disease in worsening disease state than macroscopic changes on imaging. But we did not find anything significant with respect to imaging changes. Now, perhaps most interesting for us, we also stratified patients according to treatment initiation by the treating physician. So what we saw here is that there was no significant change in spirometry parameters despite a perceived clinical need for additional treatment by the treating physician. So the person that knows this patient's disease best felt there was a need to add extra treatment, but that was not necessarily shown on spirometry. However, there was still a decrease in X5, an increase in FRES, and an increase in AX. So these changes, again, are consistent with what one would expect in worsening ILD. And it's interesting to see that there are changes reflected on the oscillometry that are not being seen by spirometry, but are being seen by the clinician. Finally, we also did the same sort of analysis looking at a composite outcome. And again, what we see here is if any of these three parameters were present, again, there was no significant change in spirometry, but a decrease in X5 and an increase in AX. So overall, what we concluded from this analysis here is that oscillometry may be sensitive to some clinically relevant changes in ILD that is being detected by clinicians in terms of just clinical impression and is leading to changes in treatment, but is being missed by spirometry. So global conclusions from this, we see that first off, oscillometry parameters, and particularly AX and resonant frequency, are well correlated with FVC in patients with ILD on repeated measurement. These correlations persist over time, and the relationship between the correlated parameters is unchanged as a function of time, suggesting that that oscillometry can be used as a tool for longitudinal monitoring in this cohort of patients. And finally, we see that oscillometry parameters, particularly AX and X5, may be able to capture clinically relevant changes in ILD status that are appreciated by clinicians through clinical gestalt, but are not being detected by spirometry, which suggests that there may be an added benefit to the use of oscillometry even above spirometry, and it may potentially lead to faster initiation of treatments that would otherwise be clinically more warranted in this population. Thanks.
Charlie first.
Yeah, that is a really interesting study. With all due my clinical colleagues and their clinical gestalt.
Disrespect, no.
Oh, wait. That is such a fuzzy statement. If one of these characters had said something to be like that, I'd be quizzing them about what is it? Is it the phase of the moon or the, whatever? What are they seeing that correlate? And you didn't show any data, but what are they seeing that correlates with oscillation?
So that's, I mean, I guess that is the question. It's not entirely clear to me, but I would imagine that, a patient is more than simply a PFT. And there are other factors that are relevant to the patient's disease status beyond just the numbers that we're seeing on PFTs. So to me, I think we've been talking about it kind of all day. I think, I can't remember your name, but no, not you. Yeah. You said it very clearly early on that we don't always necessarily know the physiological basis of things, but we correlate values and we see changes.
Well, if you're going to write this up,
yeah,
you're really going to ask you that. So I would sit down with these guys and try to nail them down a little bit more about what it is. The second is a comment, and that is that saw a study about a year ago where they interviewed a whole bunch of physicians who take care of ILD folks, and their number one thing they follow is closely followed by DLCO, and everything else is much less important. So what you're saying, you're promulgating the idea that we could replace FEC with oscillometry. And I'm thinking to myself, that's gonna be a hard sell.
I don't necessarily know about replacing, but perhaps adding to.
Right,
be
so
better.
that gets back to my first comment. And that's why you gotta tie that up.
So if I could just comment about this. So Rob did a very nice progression score that doesn't just look at FVC. He looked at, did the patient symptom progress?
Yeah,
Did the radiology progress?
yeah.
Or did the management change? So as clinicians, we don't just look at FVC. We look at, is my patient worse? Is my patient more hypoxic? Is my patient radiology getting worse? And I also look at the FVC. So in that paper that Rob has written, he like really describes how he comes up with this progression. And if we want to show that, which is what our hypothesis is, that oscillometry is more sensitive to change than spirometry, we can't look at a progression criteria that's only based on FVC as what we're doing now clinically, which is what we're kind of trying to get at.
I'm passionately interested in this because my father died of IPF and my best friend from college has it. And I look at his results every time he goes sees the pulmonologist. And I'm doing exactly what you're talking about. I want, how are you feeling? How are you coughing? What does the PFT show? And to decide whether or not they need more help than they're getting.
You're practically clinicians.
Oh, God, that's a scary.
Go ahead.
So, question and comment. Comment is, I showed up, Charlie, in 2014 at ICLAP, having started oscillometry in March of that year with 60 patients and so, and said exactly that to ICLAP. Based on this, you should be replacing the course of the FBC with AS. I think, why don't you guys study it? They did nothing. I did the same thing in 2016. I stopped going to ICLAP. Thankfully, Deborah has taken up the cause. And the question I have is just a naive clinician. Is the Box-Cox transform the same as a lawn transform, or is it different? How is it different?
It's a little bit different. So essentially, the model, it requires a little bit of math. But essentially, yeah, so depending on, you essentially have to take the data points and then you optimize kind of proximity to, it's complicated. But yeah, so partially it's lawn.
It's just because you get your plots from
yeah.
lawn of AX.
Yeah, many of them are.
And I also wanted to know, what was the absolute change in AX you were seeing that was a 0.4 lawn? What is the real numbers?
So first off, yeah, to better explain, yeah, the math is confusing to me as well, but I have a citation that I can share with you if you want afterwards. But depending on the factor that you get out of your initial optimization step, it either becomes a lawn transformation or an exponent or an inverse exponent. So that's that. In terms of the log that you're talking about, the 0.4 that we're seeing is, you're referring to the.
Is it like a 10 centimeter water per liter difference, or 20 centimeter water liter per liter?
Yeah.
Over 2 times.
So looking at
measure on average.
So looking at the statistically changed group where there's stratification by symptom severity, what we're seeing is approximately a 40% increase in AX, which I think you mentioned in the Delphi study that was similar to your CID.
Bronchodilator, but that's another.
Yeah. Anyway.
Yeah, just a real quick comment. So thank you. Wonderful work. And as someone who has worked on many failed programs in pulmonary fibrosis, it's great because we all know that I can show some differences in FDC in a short study, and then those programs go on to phase 3 where they fail. Because we all know clinically that when I see that patient in clinic, they're doing worse and their spirometry isn't changing. So this is incredibly important data I would say out there. It's something that for future clinical trials in IPF is incredibly important. So please, I beg you and Deborah to please get it published and out there, get the debate started so that we can move forward with something other than FVC in clinical trials.
Thanks.
Last question.
It sounds like though the clinical assessment of worsening was not well standardized among clinicians. This is retrospective
It was
data,
more
right?
retrospective though.
Retrospective.
That portion, yes,
Yeah,
because
yeah, so
it's
that's-
based on chart
So
review, yes.
that's, the need to sharpen that up in terms of, assessing dyspnea by a questionnaire or the patient
Mhm.
or a 6-minute walk collection or some other management thing. But did you present trajectory of FVC versus trajectory of the oscillometry, I guess the axe, right? Whereas you show a sharper decline in one versus the other, that also would be helpful.
Yeah,
I know
didn't
it's correlated, that with you regressed one on the other, but.
I showed the correlation between the values. I didn't show a specific time.
What I mean is if
trajectory.
you could show with this clinical worsening, a sharper drop off that you can pick up, because we're also a situation where someone might be getting a little worse, more short of breath, but the vital capacity hasn't changed very much, nor the diffusion,
Mhm.
and you wait for the next measurement.
Mhm.
So that might be something showing that trajectory. And also, what was the time course? Was it all 1 year or just somewhere shorter than a year?
Yeah, so it was somewhat variable.
Yeah.
It was minimum of 6 months, but on average, it was approximately 1 year.
But yeah, so maybe a little longer for the full cohort might make it clearer too. Just a couple of comments.
What did I have to move? I'm sorry.
Oh,
Thank you.
Thanks, Ellen.
So, like to call on Dan Nguyen from McGill University. Yeah. So let me a second. Is your topic? Somewhere.
We shouldn't.
Hi, everyone. My name is Dan. I'm a master's student at McGill University, working under the supervision of Dr. Brian Ross. And I'm going to take it back to obstructive lung disease and oscillometry and talk to you about a project we recently completed a data collection for, investigating the assessment of optimal inhaler strategies in the management of exacerbations of chronic obstructive pulmonary disease, or COPD. Just to come back to a little background about COPD, the latest global definition of COPD is that it's a heterogeneous lung condition characterized by chronic respiratory symptoms, notably dyspnea or breathlessness, but as well as cough, sputum production, and or exacerbations of COPD, due to abnormalities of the airways and or alveoli that cause persistent, often progressive airflow obstruction. Now, the main pharmacological treatment for COPD includes long-acting bronchodilators that may include a long-acting muscarinic antagonist, a long-acting beta agonist, and there's also emergency or rescue inhalers that are prescribed to patients with COPD to use in cases of emergency, per se. This is a very common disease in Canada. It's estimated to affect 1 in 6 Canadian adults aged over 40 years old. It's the third leading cause of mortality and morbidity worldwide. And in the last 20 years, the hospital care burden associated with COPD has increased by 48%. In fact, COPD is the leading cause of hospitalization in Canada for any chronic disease. Now, why is that? Well, if we look at the main treatable traits for COPD, being dyspnea or breathlessness, exacerbations are really the cause here. What is an exacerbation? Well, it's an acute worsening of respiratory symptoms, including dyspnea notably, but as well as cough and sputum that results in additional treatment like hospitalization. Now, this can be caused by bacterial infection, viral infection, air pollution. We talked about extreme temperature changes this morning, like heat waves. And the main course of treatment for an exacerbation of COPD includes oral corticosteroids and antibiotics. What about your inhalers during an exacerbation of COPD? What do we do about our emergency inhaler as well as our regular inhaler? Do we give patients with COPD more of their emergency inhaler while they're going through an exacerbation? Are there uniform evidence-based or guideline-based approaches to inhaler treatment during an exacerbation of COPD? Well, if I refer to the latest things that GOLD, the GOLD initiative, the COPD international community has said about inhaler strategies during exacerbation, although there is no high-quality evidence from randomized control trials, it's recommended that short-acting bronchodilators are the initial bronchodilators for acute treatment for COPD exacerbation. With regards to long-acting bronchodilators, there are no clinical studies that evaluate the use of inhaled long-acting bronchodilators with or without inhaled corticosteroids during exacerbation, though we recommend continuing these treatments during exacerbation or to start these medications as soon as possible before hospital discharge. So basically, not really. We don't know. So what is the optimal inhaler strategy during exacerbation of COPD? To answer that question, we wanted to leverage for those of you who aren't aware, that's Dr. Ross.
That's why you guys are laughing.
What nice legs your boss has.
So to answer the question, we wanted to leverage oscillometry as this much easier lung function test, as well as a highly sensitive lung function test in patients who are going to be exacerbating, who we're going to find before they take their inhalers, which really means getting patients who are hospitalized in the wards here in Montreal on the Royal Vic at 7 a.m. So we've included patients with COPD who are over age 40, they're former or current smokers with a 10-year history. They have to have a spirometry confirmed diagnosis on their chart, but they can be of any severity. And they have to be prescribed both long-acting and short-acting bronchodilators. And their exacerbation of COPD has to be the primary cause of hospitalization. Furthermore, they also have to be able to do oscillometry without the use of supplemental oxygen. And with all that information, we want to be able to compare, as our primary objective, oscillometry obtained markers of expiratory flow limitation before and after the use of short-acting bronchodilators alone, and then following the addition of long-acting bronchodilators to short-acting bronchodilators in patients being treated for an exacerbation of COPD. The main outcomes we're looking at here, or markers here, are reactants volume loop area, or AXV, and mean inspiratory minus expiratory total respiratory system reactants, or mean XRS. Our secondary objectives were to investigate patient-reported dyspnea scores before and after the use of both inhaler strategies, and also to collect any information on side effects associated with the use of combined short-acting and long-acting therapies. The actual study visit looks like this. We come at 7 a.m. At baseline, when they haven't taken any inhaler, we ask them their current dyspnea, and then we perform a set of oscillometry, which includes about 6 tests. No, I wrote 4 here. It was 6. Then they're asked to take their short-acting bronchodilator. We wait for the effect to maximize, and then we repeat the visual analog scale for dyspnea. We repeat oscillometry test, and then finally they take their long-acting bronchodilator, repeat the same things. It's over, they get $20. For those of you who are less familiar with the visual analog scale, though, that was already shown this morning, it's a scale anchored from 0 to 10, with sometimes you do use numbers, where 0 is no shortness of breath, 10 is maximal shortness of breath ever experienced, and about a 5 is what's considered very severe dyspnea in patients with COPD. Moving on to our results, to give you some idea of our recruitment strategy and some of the feasibility of doing oscillometry in patients who've been hospitalized for an exacerbation, we approached about 55 patients with COPD and 47 of them agreed. So we had about an 85% recruitment rate. Of those people, 37 fully completed the study. We had 6 people who didn't finish because they couldn't complete tests, or 4 people who just had a bad night and ultimately never finished the study. Of those participants who recruited, we mostly had female, we had a little more female participants than male participants. They're about 71 years of age. We have a misleadingly average BMI here, but I'll tell you that the majority of them are actually on the lower end there. They have a pretty high smoking history. There was a good mix between active smokers and ex-smokers. The majority of patients had a diagnosis of GOLD 3 or GOLD 4 COPD. And what I want to really highlight is that these are patients who are very frequent exacerbators. Someone who have frequent exacerbator COPD has 2 in the last year. These patients had on average 3. And not only do they exacerbate frequently, but they're frequently hospitalized. To give you an idea of what their actual inhaler strategy was, the majority of patients were on a combined short-acting bronchodilator, and they were on single inhaler triple therapy as their long-acting bronchodilator. Here you can start actually looking at our oscillometry results. This is data from participant 1, where you can see the monofrequency reactants versus volume loops, or AXV values, at baseline, then after taking the short-acting bronchodilator, and after their long-acting bronchodilator. But when we look on average, we actually found out that there were no differences. So on the y-axis, you can see the AXV values. On the x-axis, you can see each time points, which was a little surprising to us. But when we adjust for sex, age, and FEV1, you can actually see there was a significant difference in AXV values following the short-acting bronchodilator and long-acting bronchodilator compared to baseline. When we look at XRS, we didn't have to adjust immediately. And you can see that there was a significant difference in XRS following the administration of short-acting bronchodilators and their long-acting bronchodilator. Interestingly, when you adjust as well, you can see there's an even bigger decrease in XRS following their long-acting bronchodilator compared to their short-acting bronchodilator. Finally, in terms of our secondary outcomes, you can see that following short-acting bronchodilator administration, dyspnea scores decreased, as well as when they took their long-acting bronchodilator as well. And as a reference, the minimum clinically important difference for their visual analog score for breathlessness would be a unit of 1. And so from baseline to both inhalers, it was about 0.9. Again, when we adjust for age, sex, and FEV1, there's a even bigger decrease in dyspnea following the administration of long-acting bronchodilators. In terms of side effects, it's a very easy slide to talk about. There were none. So in conclusion, both short-acting bronchodilators alone and long-acting bronchodilators plus their short-acting bronchodilators approached significantly improved expiratory flow limitation markers and visual analog scale obtained dyspnea scores compared to baseline. When adjusted for sex, age, and FEV1, taking both inhalers significantly improved expiratory flow limitation and dyspnea scores compared to short-acting bronchodilators alone. So our results support using both inhalers in managing exacerbations of COPD for better physiological and symptomatic outcomes. And I just wanted to repeat again that our AXV values only improved when using having adjusted for age, sex, and FEV1. Just before I wrap up, I just want to acknowledge some of our study team. Alexandre Siu did the majority of the data collection here. Giuliano also was involved with the screening and data collection as well. Sai did the stats. Olivia was involved in conception. Obviously, Dr. Ross is the PI and let us present today. And I also want to acknowledge the Royal Vic Hospital treating team who made it possible to identify and recruit patients for this study, and as well as the patient participants who completed oscillometry many, many times. Questions?
Thank you very much. I'm going to take the moderator's prerogative and just ask the first question. The results that you've shown us are all monofrequency recordings and interbreath. Were there any differences that you saw with the spectral?
So we have the spectral results, but we want to redo them with like the latest methods. So we didn't want to look at them today in case they were not as accurate as they could be. So I can't tell you about them today. But we will do that.
Please.
So I know that you compared everything versus FEV1, wondering what happened, like some other parameters like FEF 2575, or is something that no one compared anymore to those ones?
We definitely could for them. We'd also have to go back and check the charts, but we could definitely do that. We went with FEV1 for this analysis because it's a more common adjuster.
But you didn't do the spirometry at the same time that you did.
So it would have been
okay.
on the chart, yeah.
Yeah.
I have a couple of questions just regarding the protocol.
Yeah.
How long after the short-acting bronchodilator did you make the measurement? And likewise, how long after the LABA/SABA did you make the measurement? And which long-acting bronchodilator were you using? Was it formoterol or was it something else?
So for your first question, it was 15 to 20 minutes,
okay,
which is pretty in line with what you do with spirometry. For the long-acting bronchodilator, it was pretty much immediately afterwards. We did the oscillometry, and you asked which medication.
Well, because formoterol acts quickly like albuterol or salmeterol, but some of them have a longer onset, like salmeterol. I was just wondering, was it a mixture of different ones that were?
It was a mixture. Yeah,
okay,
I would have to check which one.
And then how long after the short-acting bronchodilator was administer and then measure with the long-acting, because you might get some carryover effect. The short-actings will last about 4 to 6 hours.
Fair question. It was all done within a 1-hour visit.
Okay.
So it would have been, 20 minutes afterwards.
Charlie and then Eric.
As you saw llamas, I mean, people thought about doing llama and lava
Llama.
because the mechanisms are so different.
Yeah. I mean, again, so there were definitely some people who did have like a llama lava, or sometimes they would have the individuals, but most of them would have been on a single inhaler.
But I think it's an interesting question.
Yes, yeah. So we do have that data, but it's just like not in similar numbers.
when you're presenting those box plots, or did you kind of preserve, you have matched data among participants, right? So you can't like average at different points, you know, not including the, you know, that these 3 points are on that person. Like, you have those graphs where you, you know, show like change after within an individual.
Yeah, so those, it's,
That you kind of fit that in.
yes.
Okay, that's good. That's just good to know that's done that way. Okay, thanks.
No questions online? Brett? Questions online?
Nobody's got their hand raised, so, no, but I do see the next speaker online.
Thank you very much. Thank you. Mhm. So, I'd like to welcome Dr. Yvonne Cherez Ojeda. I hope I'm pronouncing that correctly. From Ecuador, and if you, I think I've stopped screen sharing here. So if you could share your screen, Ivan.
Yes, good afternoon. Are you looking at the presentation?
This looks terrific.
Are you looking?
We can hear you.
Ah, okay. Okay. Good afternoon. First of all, I would like to thank the organizer, especially Ronald, for giving us the opportunity to present our study, the potential role of oscillometry in the evaluation of poor viral costs. We know that not pharmaceutical intervention, including social distance, mask wearing, shelter in place, travel restriction, and school closure, were implemented to reduce SARS-CoV-2 transmission during the COVID-19 pandemic. As a consequence, these NPs also reduced transmissions of many other infection pathogens, with substantial decreases observed for illnesses like influenza, respiratory syncytial virus, and mycobacterial tuberculosis. However, a resurgence of this respiratory illness occurred after NPI relaxation. This rebound led researchers to propose the immunity depth hypothesis. The hypothesis of immunity depth suggests that the population may have become more vulnerable to other non-COVID-19 infection pathogens due to reduced exposure to other pathogens during the pandemic. As a result, a decrease of immunity against these microorganisms could occur. A recent study confirmed the hypothesis. The immunity depth demonstrating an increase of influenza rates of more than 100 to 30% and 100 to 60% compared to historical level in winter and summer season 1 year after the global relaxation of COVID-19 restriction. But you can see that is the number in Canada. Therefore, we expect an increase in the incidence of different viral infections and probably more severe symptoms and long-lasting symptoms. Post-viral cough is characterized as a persistent cough that emerges after the resolution of viral infection, driven by complex inflammatory and neural mechanisms. It's called for careful assessment and management, particularly when it progresses into a chronic condition affecting the patient's quality of life. The chest expert cough panel classified cough according to the duration of symptoms in acute, subacute, and chronic cough. Using the PACO question format, population, intervention, comparison, and outcomes, a working group recently identified key questions regarding the management of chronic cough. They suggested that an empirical trial with inhaled corticosteroid can be considered in patients with chronic cough if there is a normal chest XR and no clinical suspicion of other conditions such as postnasal drip or GERD. In regards to bronchodilators, they pointed out that no evidence supports an empirical use of inhaled or oral bronchodilator as a standalone therapy for non-specific chronic cough. On the other hand, small airway dysfunction, SAD, is a term used to describe impairment in the function of a small airway, defined as an airway with a diameter of less than 2 millimeters, which plays a role in maintaining optimal respiratory function. SAD can contribute to significant alteration in respiratory mechanics and is increasingly recognized as a vital component of various respiratory diseases, particularly asthma and COPD. The impact of SAD on lung function is profound. It is associated with changes in airway architecture, such as well thickness and hyperresponsiveness, both of which contribute to the pathophysiology of asthma and can influence treatment response. Oscillometry allows measurement of the respiratory system impedance. Physiologically measure of this impedance quantify how easily air moves in and out of the respiratory system. It is composed of respiratory resistance related to relative properties of the respiratory system and reactance links to the elastic and inertial properties of the system. Oscillometry permits us to measure the most airways and therefore small airway dysfunction. I would like to emphasize this study where in a rat model of post-bronchiolitis chronic airway dysfunction, it was looking for how post-infection small airway lesions affects airway physiological function and if the structural function damage of the small airway persists into maturity. The author concludes that the viral airway injury at the early age may induce a small airway lesion that are associated quantitatively with a small airway physiologic dysfunction early on, and that these defects persist into maturity. In a recent publication, the authors identified characteristic pattern of SARS-CoV-2 associated co-detection, with a notable emphasis on the co-detection of human rhinovirus, enterovirus, parainfluenza 3, and respiratory syncytial virus, alongside SARS-CoV-2. The analysis showed that human rhinovirus enterovirus is the most prevalent, followed by parainfluenza 3 and RSV. Furthermore, in this line chart, we can see how by October 2022, parainfluenza and rhinovirus and RSV had a peak of detection as a simple pathogen, and there is an increase of co-detection of RSV and SARS-CoV-2. This association appeared to hold high significance during the Omicron variant era, compared to the early SARS-CoV-2 variants. For instance, the co-detection of parainfluenza and SARS-CoV-2, as well as rhinovirus and RSV, may play a more important role in the era of Omicrons than previous variants regarding clinical manifestation. we have patient, we were receiving patient with different symptoms that's previous pandemic. Therefore, we think if we expect to have more viral infection incidents, more co-infection, and maybe more severe symptoms and more long-lasting symptoms in the coming days, will be there more chance to a small airway damage? And if this is a fact, why not measure the small airway dysfunction first to then better use early bronchodilators and or inhaling corticosteroid? In order to answer the questions, we developed a study where the primary objective was to determine the prevalence of small airway dysfunction in patients with post-COVID cough. And the second objective was to determine which oscillometry parameters are most commonly altered. We conducted this study retrospectively in our center. We selected patients with dyspnea or persistent cough for more than 1 week, following symptoms of acute respiratory infection, which include such as fever, malaise, sneezing, sore throat, and runny nose from May 2024 to June 2025. In addition to demographic data, we recollected symptoms, viral PCR tests, fractional exhale nitric oxide, oscillometry results. For statistical analysis, we use SPSS, and we define a small airway dysfunction if the R5 to 20 is more than 0.07, the X5 less than minus 0.12, the frequency of resonance more than 14.2 Hertz, and the area under the reactance score more than 0.44 kilopascal. It is a pleasure for us to present our preliminary results. A total of 296 patients were evaluated in our center, and 149 had post-viral cough. Almost 64% of the patients were female, the mean age being 42 years, the mean BMI almost 27, and the most of our patients were Hispanic. Please look into these results. We observed that with the R5 to R20 parameters, almost 62% comply with the SAT criteria. However, if we look the other parameters, such as X5, we have 100% of affection, with 8X, 90%, and with FRES, 85%. We decided to use logistic multivariate regressions where the dependent variables were gender, ethnics, BMI, and age categories, and we found that only being female increased the probability of presenting SAT on a 2.3 odds ratio. Moreover, 52% of our patients had a FeNO, and 16% of them reported a high level of FeNO. In addition, only 17% were practiced viral tests, and out of those, the 72% had positive tests for viral infection, being the most frequent viruses, influenza, COVID, and RSV. Finally, small airway dysfunction. According to the cough classification, we found that 43% have acute cough, 37% subacute, and 20% chronic cough. In conclusion, first, post-viral infection may increase SAT Second, we recommend using oscillometry in all of patients with poor viral cause. First, we use the use of bronchodilators and or inhaling corticosteroid could be part of the early treatment. And finally, females have double the chance to develop such post-viral infection. We are still working on this project, and I would like to invite all of you to collaborate with us. Thank you very much for your attention.
Thank you very much for this, Evan. Jason Bates has the first question.
Yeah, thanks. Very interesting. It seems to me, tell me if you think there's anything to this, but it seems to me as if a lot of these patients have some sort of persistent airway inflammation because they had elevated FeNO. They also had elevated AX, which is the sort of thing you'd expect to happen when you have inflammation in the small airways that predisposes to liquid plug due to excess mucus, thickened airway walls, de-recruitment, that kind of thing. If that's the case, then some kind of anti-inflammatory treatment like ICS kind of makes sense, doesn't it? Did you find it had an effect?
I invite my team because I have little problem with my English, but my team is very young. They speak English very well. Okay. Please.
Bring him closer to the line.
Have him come closer to your mic so that we can hear him.
Tell him to come closer.
It just grows.
Get closer.
Can you come closer to the microphone to your microphone so that we can hear you?
Come closer.
Come a little bit closer because yeah.
You tell me the question, please. Again.
Maybe Jason, if you could, I'm sorry, I was distracted. So if you can.
It was just an observation. You had elevated FeNO in a lot of these patients. You had an elevated AX. But more than elevated resistance, right? And that is consistent with, doesn't prove it, but it's consistent with diffuse de-recruitment, which can happen if you have excess mucus or inflamed airway walls that predispose to the formation of liquid plugs across the airway, de-recruits the lung. In other words, it's sort of painting a picture of general airway inflammation. So I'm wondering if these chronic cough patients post-viral just have a persistent airway inflammation, which for some reason has not gone away. Should have, perhaps. So maybe corticosteroid makes sense.
So
we only have 16% of patients with FeNO elevated.
16?
Yeah.
Oh, not so many.
Exactly. The more of that as low FeNO. And in the patient who have high FeNO, we have sense to use inhaled corticosteroid. And probably in this case, we need to use different small size of the particle for medication. But the huge group, we don't have FeNO elevated. The idea is to use only bronchodilators, could be.
And this consistent because
It
is consistent because most of the patients have a viral infection that is consistent with low FeNO.
Oh. So it's not an.
Actually, for
do you have any follow-up data on these patients to show improvement in the oscillometry parameters, at 3 or 6 months after your initial?
Yes. Thank you for this question because we study are ongoing, and the idea is to measure again on the 3rd and the 6 months because we expect that in the future we have patients we have persistence of the small airways because we have experience with long COVID patients who had after severe COVID affection, they at the moment after 4 years, they have continued with a small airway dysfunction.
Thank you. Any other, please?
I think the issue with the phenol is not surprising because if you have a neutropenic condition, you have secretion of all the peroxides there, you know. Karina and Yvonne have demonstrated that basically the scavenger phenol to create a nitroxyl peroxide, you know. They're often, that's why probably we see significant number of decreased phenol, although, you know, we see impact of small airways.
And maybe if I can follow up a little bit on that, is there any evidence that these patients with the high elevated phenol that they're asthmatic?
Some of the patients, well, in this case, only was a patient with no comorbidities. There are another side of patients that have some comorbidities, including asthma, that also experience some exacerbation following a viral infection. But in this data set, this is not it was not the objective, so we don't have that information. But in our center, we see that some patients have some flares and are asthmatics, and also the phenol maintains low because there is a viral infection.
Thank you. Jeff Maxim has a question.
Yeah, just a question. I noticed that in your logistic regression analysis, you included many factors, and one of the factors that came up as being very important was sex. But you didn't include height. And for oscillometry, height is a very strong predictor of resistance and reactance, particularly if you're going across a large age range or you happen to have a population with a wide range of height. So I might, do you know if you have basically more oscillometry positive results with shorter patients in your group by any kind of feel or gut feeling that you might have gained during the study?
If we use another kind of logistic regression.
No, the same logistic regression, but include height as one of your variables, because height is an important predictor, just as even more than sex. And you found sex was an important factor. I think you should include height.
Yeah.
Okay.
Yeah, it is correct. And we usually use the CT score, but for this from the Gochikoa-Rangel equation, but for this study we use the fixed cutoff of the parameters, and absolutely the height can be a predictor. Thank you for your comment.
We use logistic regression using another alteration parameter, X5.
Okay. The only significant results were for error 5 to error 20, because the others parameters of a small airway disease, I mean the X5, the frequency of resonance, and the area under the DX, the area under X, were not significant. There was no significant predictors in that variables.
Okay, but you had a large number of people with abnormal values or above cutoff, but not significant, I guess.
Yeah.
I still think it's worth looking at.
Yeah.
Thank you.
Well, thank you very much. I want to congratulate you because I do know it's very difficult to recruit patients, particularly patients who don't have a chronic disease for research studies. So congratulations on your work, and thank you. Next, I would like to welcome Prakash Bihasvaran, who is coming to us from Sydney, Australia. He'll be talking on the patterns of, I hope, oscillometry and lung function impairment in patients following tuberculosis. So we can see your slides, and please, and welcome. And please, if you wouldn't mind turning on your screen so that we can see you as well.
Yes, hopefully the video is working now. And can you hear me okay?
Yes.
Brilliant. Brilliant. Well, good morning from Australia, and thank you so much for this opportunity to present our research from Sydney on the spirometric and oscillometry patterns of post-TB lung impairment following treatment of pulmonary and pleural TB. Tuberculosis is an airborne infectious disease caused by Mycobacterium tuberculosis. It has a global incidence of about 10 million cases per year, and it remains the leading infectious cause of death worldwide, accounting for over 1.6 million deaths each year. And whilst tuberculosis itself is treatable and curable, over half of treated patients experience post-TB sequelae. And now, with over 150 million TB survivors worldwide, the issue has started to gain real recognition. So in 2019, the first post-TB lung health symposium was held, at which time definitions and clinical patterns of post-TB lung impairment were described. Since then, there have been 2 further symposiums and much progress into this important field. The current clinical standards recommend that all survivors of TB are assessed for post-TB lung disease with a history, clinical exam, imaging, and functional testing, which includes respiratory function testing with or without oscillometry. However, there are actually very few studies to date that explore the role of oscillometry following TB treatment despite this recommendation. The population of TB that we see in Australia is not dissimilar to that of Canada's. Both countries have an incidence rate of about 5 cases per 100,000, which occurs disproportionately in our first-generation immigrants and our Indigenous populations. And as we know, oscillometry can be portable and easily performed by patients from a range of age, cultural, or linguistic backgrounds. So even if careful instruction or communication is difficult, which makes it ideal for our busy or mobile TB clinics where language barriers are often an issue. However, as mentioned, there remains a real paucity of data around the use of oscillometry in actually assessing post-TB lung disease. So our research aimed to characterize the population of tuberculosis in Sydney and assess the impact of TB on pulmonary function testing and probe the role of oscillometry in assessing patients with post-TB lung disease. And we hypothesized that ventilatory abnormalities would be common and that oscillometry would show a similar rate of abnormalities compared to spirometry. So we've conducted a single-center retrospective study out of the Parramatta Chest Clinic, which is the largest tuberculosis center in Australia. So all patients who had completed treatment for tuberculosis through the Parramatta Chest Clinic were offered pulmonary function testing regardless of their symptoms. And we conducted a chart review of the 122 patients who went on to finish treatment and then underwent pulmonary function testing at a fully accredited respiratory function laboratory in Sydney between 2018 and 2025. We collected data around demographics, spirometry, lung volumes, gas transfer, with Z-scores calculated using GLI race-adjusted reference equations, along with oscillometry data that was collected using a Resman Pro device, and data reported with Z-scores, again calculated using the Usvin et al.'s reference calculations. So in total, we had 122 patients, the majority of whom were male, tended to be younger with a median age of 32. The population was otherwise reasonably healthy, with only 16% having any prior history of lung disease, and the majority of patients had never smoked. So in general, it was a relatively clean population beyond the history of treated tuberculosis. In terms of ethnicity, over half of the patients fell into the other category of ethnicity, heralding from the Indian subcontinent and surrounds. Now, all patients had fully sensitive tuberculosis that was treated successfully with standard multi-drug tuberculosis therapy. The majority had pulmonary TB only, so that affecting the lungs, whilst 8% had pleural TB, so affecting the lining of the lung. A further 8% had both pleural and pulmonary tuberculosis. And finally, 8% had pulmonary tuberculosis with other sites such as gastrointestinal or lymph node involvement. Now, the following graphs capture the Z scores of our entire cohort on lung function testing and oscillometry. And we can see on the left that there was a tendency towards a reduced FEV1 and FVC, a reduced TLC and DLCO, with quite a wide range from supranormal to severely impaired. There was a tendency towards an increased R5, reduced X5, and an increased AX, with again some patients demonstrating quite severe impairment. So on the right, we summarize the normal and abnormal lung function testing on the basis of a Z score that was less than minus 1.65. And we can see that abnormalities in lung function testing were very common. In fact, only 41 patients had normal lung function testing. 54 patients, that is just over half, had abnormal pulmonary function tests. Of these, we can see that the majority had a restrictive picture at 45%. About 22% were obstructed to varying degrees, 9% were mixed, and 12% had preserved ratio with impaired spirometry, and 12% had an isolated DLCO reduction. What about the 37 patients that had an abnormal FOP? So we can see that the predominant abnormality in these patients was that of an abnormal area of reactance. However, the group was heterogeneous, with a number showing increased resistance at 5 Hertz in reactance. And most patients with abnormal FOT did also have abnormal spirometry, but curiously, there were 12 patients in whom they had abnormal FOT but normal pulmonary function testing. And focusing in on this group, we can see that 7 had an abnormal R5, 2 an abnormal X5, and 11 out of 12 had an abnormal AX. Curiously, this subgroup was majority female, so 10 out of 12 of these cases were female, with only 1 patient having any history of lung disease in the form of a pulmonary embolus 5 years prior. They were young with a median age of 28, and the majority of them did have symptomatic tuberculosis at time of treatment. And finally, the 29 patients who had normal but abnormal PFTs were also a heterogeneous group with predominantly restriction, but 25% had mild to moderate obstruction, 21% had an isolated DLCO reduction. So these results point towards otherwise young, healthy patients, all of whom had access to free, publicly funded, high-quality healthcare, and all of whom had adequate microbiological treatment of their tuberculosis, still demonstrating a significant burden of lung function impairment. So the combination of oscillometry in addition to spirometry led to an additional 12 cases of abnormalities being captured. But the study is not without its limitation. We wondered if the high prevalence of patients whose heritage stemmed from India, Nepal, and surrounds were not well represented in spirometry and oscillometry reference ranges, which may have led to an overestimation of restriction in our population and an overestimation of an abnormal area of reactance. Further, as a cross-sectional study, we do not have follow-up data at this stage on whether these impairments do persist over time. And finally, we do not know if these physiological impairments translate to meaningful symptoms in our patients. So in conclusion, post-tuberculosis lung impairment is common despite adequate microbiological treatment of TB. And so our cohort, whilst predominantly young, otherwise healthy, with access to good healthcare, still had a significant burden of lung function impairment. And whilst oscillometry was not as effective as detecting abnormalities as spirometry, its role in post-tuberculosis lung disease still remains unclear. And in recognizing this really high prevalence of physiological abnormalities, we hope that further research can be done to identify and treat the huge number of patients with post-TB lung disease who at this stage remain grossly under-resourced and understudied. Thank you.
Thank you very much. And I will admit that I'm also quite surprised that TB remains such a problem in this day and age. I have two questions for you, and thank you very much for the study. Very, very interesting. I'm particularly intrigued by that population that you showed us of abnormal oscillometry, but normal standard pulmonary function studies. And even if you remove that 21% whose sole abnormality was reduction in DCO, you still had something like 20 odd patients who had abnormal oscillometry and normal standard PFTs. And so I guess my question is, do you have, what is your, do you have any thoughts in terms of what is some underlying mechanisms of that? And then the other question I have is, do you have any CT analysis to in terms of sort of indication of what actually the structural sequelae are post-treatment?
Those are two great questions. In terms of the abnormal oscillometry, but normal pulmonary spirometry, removing the DLCO cases, it still came to about 12 with abnormal oscillometry, but normal other metrics. And of those 12, we don't have a good idea what was driving it, whether we know oscillometry and spirometry measuring different things. As to what the actual difference is remains unanswered in this population. We do wonder if, given the majority of the cohort was actually male, whereas almost all of these were female, whether it reflects the reference ranges rather than an actual pathology, but it's hard to say at this stage. In terms of the radiology, that will be really helpful to answer that question, and currently collecting data on the radiology, both pre and post-treatment in all of these patients. And ideally, when characterizing post-TB lung impairment, we want not just their lung function testing in the form of spirometry, DLCO, oscillometry, but we also want their radiology, ideally in the form of a HRCT, which is currently under collection. And the other two things that would be really useful would be symptom assessment, as well as echocardiography or looking at their pulmonary vasculature, which unfortunately we don't have that data available.
And maybe I can draw some of the other folks in the audience who've been doing a lot of work with the reference ranges, because my reading of the literature is that sex and age really don't play a big role in determination, and it's really primarily height. So I wonder if I can get some comments. Ron.
Yeah, no, I think that is key, because I mean, the issue with growth rates, so if we could normalize, have local reference to it.
Just a second, can you hear him?
Not quite, it's very, very soft.
Yeah.
No.
In the absence of good reference equations, I think we're going to be stuck, honestly, which is why we have to go ahead and do it. Are you guys on your end doing any local reference equations in your population?
No, not that I'm aware of, at least.
Okay, because with Shannon Simpson based over there, I would expect you guys to be more productive. But I think on a global scale, we're pretty lazy on that respect. I think that something like this should be used as yet another request to the greater community to make your data available, because there are many people like me who have vast sets of oscillometry data, and we need to take our healthy individuals, sort them out, organize them, and then share them with the GLI, because only by pooling these stuff, we're going to approach the numbers we need to be able to standardize these studies and make them more understandable. Because at the end of the day, we're stuck with this question.
David, and then I think
I will go back to that discussion about the instrument, because yes, one move the other, the difference between lack of the reference standard or equation, or the difference of the instrument.
Yeah,
how are we gonna build that?
We won't answer that question until we actually do it for instrument, but I think for now, in my own mind, I've sort of put it on the back burner only because the instruments agree very well at low impedances.
Yes.
And when we're doing healthy people, we're essentially measuring low impedances. So that's how I get around that and sleep at night saying I'm not being too dishonest. But you're right, we do actually have to do that study ultimately.
David?
Prakash, you looked at a mixture of patients who had tuberculosis of their lung parenchyma as well as their pleura. I was wondering if you separated them out just to see if indeed more pleural TB resulted in more restrictive pattern.
Yes, actually we did. And the pleural TB, so it was 19 patients, they had a predominantly restrictive pattern of impairment, especially on their spirometry, their plethysmography, without so much a DLCO impairment. Within that population, we actually do have the radiology data, and it's a really interesting picture where we see all 19 patients had radiological abnormalities initially. Post-treatment, most of that melts away as pleural effusions and tuberculosis respond really well to treatment with just some residual pleural thickening on x-rays. But despite that radiological improvement, almost all of them still had persisting restriction on their lung functions, along with a very similar picture of an increased AX and a slight increased R5. We didn't see much difference between that and the pulmonary population, but we also wonder, a lot of pleural TB have undiagnosed pulmonary TB in addition.
Thank you.
So Leonard has a question.
Well, thank you, David, for asking. It was mine as well. That was good information. I have one comment, and that is Busselton, south of Perth. They actually are collecting a lot of normal data. It's maybe not, it's sort of skewed maybe to somewhat older people, I believe, but at least they're collecting. So there's some activity on that in Australia. I don't know how representative that would be for your area, but yeah.
And Jason, did you have a question?
It's
Okay. Maybe one last question. Is there any comparable data, or do you know of anyone who's collecting other data with other sequelae of pulmonary infections? So other bronchiectatics or other things that are not non-CF and non-TB?
Right. I'm not up to speed within other lung infections at the moment. I know at least in tuberculosis, there's currently some work by Anthony Burns, who also works in Sydney, but he's recently released some research from 100 adolescents in Lima using spirometry and oscillometry to assess post-TB lung disease. And there's been some publications out of India as well in the last 2 years. But I think one was a cohort of about 30 patients, 20 of whom had TB, 10 were control. And the other one was 80 children.
So thank you very much, and thank you for joining us. You're going to have a lovely day, and we're going to supper. So join us next year in person.
So thank you, Chung Wai. Prakash, thank you.
Thank you.
I hope you'll be able to tune in tomorrow, although with the time difference, I'm not sure you're going to want to be up with us at 9 a.m. But Disha will be picking up where we left off, because we will have another talk on TB and the oscillometer changes associated in a much less clean population, because she's going to limit her talk to COPD. So if you can't catch it, tune into the recordings, which I'll try and post in the next month, and we'll be able to compare your two studies. And I hope you guys actually will communicate back and forth, because I think it'd be interesting for you to share.
My calculations are correct. 9 a.m. would be okay, but it's
Are you-
now that's the problem.
How are you at 9 a.m. our time?
I think that should be okay. That should be, I should be able to join for that. That would be
Okay, then
interesting.
we're expecting you. And if
Yeah.
you're not there, we'll phone the home.
Brilliant.
So we, on the other hand, are going to wander down the hill and have a drink and then have supper. I don't know what the weather's doing out there. It doesn't look as nice as it was earlier, but maybe it's only wet on the ground. Let's keep our fingers crossed. And then tomorrow we'll start off again at 9 in the morning. So I want to thank everybody for wonderful talks, great comments, an amazing discussion. And let's really continue the theme of discussing, sharing, networking over drinks and supper. And like other years, I'm hoping that there will be many new projects that might come out of what's going to happen this evening. So enjoy, everybody, and thanks again. And especially industry, thank you very much for making it happen. We will have a chance to thank you more intimately as we share cocktails.